Okay, can I start now?
Yes.
Yes. Okay, so good afternoon, everyone. I'm here again to welcome you all. So today is the second day of our quantum computing workshop, that is Qubit workshop. So Lokesh will be taking over this session. So Lokesh, will you start?
Okay, yeah, I'll start now. Let me share my screen. Okay. So now, am I audible and everything is fine, right? There's no
Yep.
problem.
Yep. You're good to go.
Okay. Well, yesterday some people were asking about the Hilbert space. I actually started rushing from there, from the slides of Hilbert space. Let me get that. So I'll start from there. Okay. Yeah. So actually, what I want to say about Hilbert space is that we studied what vector spaces were, right? We studied that there were some axioms that we follow, right? So Hilbert space is also a vector space. It is same as the vector space. It contains vectors that are collected based on these axioms, but along with it, it has the notion of inner product. Okay, along with these axioms, what we can do is that we can take the inner product of those vectors inside the Hilbert space. This might seem a bit odd that why do we need a separate space for it, but it is as it is. Okay, so I'll explain it in a proper way. I'll give you some documents about it through Discord, and things will get clear. Okay, so next thing is concept of linear combination. Now, what is linear combination? What combinations mean is actually pairs, right? We keep things in pairs, in couples, and what we call them is combination, right? Simply we can say it. Now, linear combination is putting things linearly and putting a plus sign between them. So we call it a linear combination. Okay, I'm just speaking something. I'm speaking gibberish here, so I'll just do. Wait a minute. Yeah. Okay. What I'll do is go through the definitions now. Okay. So it is an expression of a set as the sum of its elements, each multiplied to individual scalar coefficients. So definition simply makes sense, right? We can have a set. We know what a set is, right? It's collection of elements. So we can have a set, and now we have to express it. Earlier, what we did was we used this representation for sets, right? We used to represent sets like this, okay? But we can also express these sets as sum of its elements. So let us do it. Let us take a set F which contains 2 apples, 3 bananas, and 1 tomato. Okay. Now, if I had to write it in the form of linear combination, what will I do? I'll write it as F is equals to 2 apples plus 3 bananas plus 1 tomato. Okay. So what we did was we expressed this F as combination of its elements, apples, banana, and tomato, multiplied to scalar coefficients. And in this case, these scalar coefficients are telling the number of elements there are. There are 2 apples, there are 3 bananas, and 1 tomato. So we expressed the set F as linear combination of its elements. Simple thing. Now, not only a set, but we can also express a vector as other vectors, as linear combination of other vectors. Okay, and the example for it is here. A vector v can be expressed as sum of other vectors multiplied to some scalar coefficient. Let us see how. So here is a vector v that is 4, that has x component 4 and y component 6. Okay, now 4 can be broken down into 1 and 3, 1 plus 3. So actually I just skipped a little step here, which is simply just breaking this down. I can say 4 plus 3. Sorry, uh, I just did it wrong. I can say 1 plus 3. I can break down 4 into 1 plus 3. I can write. Then 6 can be broken down into 3 plus 3. Okay, so this was the step I missed. And now I can break these down as 1 plus 3 plus 3 plus 3. I am breaking this whole vector here into two vectors. Okay. Now, if you work backward, if you calculate it backwards, what will you get? 3 plus 1, 4, and 3 plus 3, 6. It is the same thing, right? Okay. So we expressed till now we expressed 4 and 6 as linear combination of 1 by 1 3 and 3 4, these two vectors. Okay. But now, where is the concept of scalar coefficients? We see no scalar coefficients here, right? What we can do now is we can take one in front of the first vector 1 and 3. So it would be same as it multiplying to 1 is changes nothing, right? So it is same to 1. This part is same to this part. Sorry, whole. Okay. Yeah. And now what else can we do? We can take 3 out of here. If we take 3 out of here, it becomes 3 multiplied to another column vector 1 1. Okay. It is also same as this. You will multiply, when you multiply this scalar inside, you will get 3 and 3. So it is the same thing. Okay. Let me just erase most of the things here. Yeah. So, so what we did actually was just representing this vector v in the form of linear combination of these two vectors, and each vector here is multiplied to a scalar coefficient. This is what linear combination means. This is how we represent, we can express any vector as linear combination of other vectors. Okay. So moving forward, this was the general formula actually that I wanted to put about any vector. About any vector can be expressed as some linear combination. You will see it is a linear combination, right? The first A's, all these A1, A2, up to AN. Sorry, all these are just scalars, and inside here are vectors v1 up to vn. Okay, so this is actually a linear combination. What we did here, this is the general representation of a vector v expressed as linear combination of a1 v1 plus a2 v2 up to an vn. Okay, this is just expressed here as summation. You will know what it is. Okay, it is just saying that from it is actually just saying that we are adding ai vi until started from I is equals to 1 until I is equals to 1 to 1 equal. Okay, let me just explain it properly. So what it does is that we have a summation sign here. It is saying that we are adding ai vi up when from the values I is equals to 1 to I is equals to n. So we are actually doing the same thing. We are starting from a1 v1 up to a n vn. Okay, this is what it says. So why are we studying this linear combination? Because see, a quantum state is also a vector. It is a vector, right? So we can use we can express a quantum state as linear combination of other vectors, and this expression of a quantum state as linear combination of other vectors is called quantum superposition. Okay. Moving forward is the concept of linear independence. So it is a very simple thing. What we learned right now was we expressed a vector as as a linear combination of of other vectors, right? But if I pick any two random vectors, okay, it would not always be possible to express them in terms of one another. Okay, if we have infinite number of vectors, we can choose from them. We can choose any one vector and express, and we'll always get among from those infinite number of vectors, we'll always get at least one vector on whose term we can express this. Okay, let me explain it like this. Suppose uh, we have a set. I can say we have a space that contains a infinite vectors, right? If I pick any vector v1 and suppose there is a vector v13, okay. If I choose to express this v1 as linear combination of other vectors from this infinite up to v infinite, I can choose any vector. Okay, I can choose any other vectors and express it. Suppose v1 becomes the linear combination of v100 plus v101. Okay, so what I did was express this v1 in terms of other vectors. Just a minute, guys. Just a minute. Okay, yeah. So what I was saying that we can, if we have only one vector, if you pick any random vector from this vector space, we will have other vectors, so many vectors that we can use to express it. Okay, but if we pick, and if I pick two vectors, if I don't pick just one vector, if I pick two vectors, like I sorry, okay, like I picked here, if I pick v1 and v13, okay. So is it always possible that v1 would be expressible in terms of v13? Or can I always express v13 in terms of v1? It is not quite possible, right? There can be times where it would be possible, it would be expressible. There will be times where it won't be. So if it is not expressible, then they are said to be linearly independent of one another. They are independent of one another. They cannot be expressed as one another. Okay. Now, mathematically, it is a bit tough. If you studied, you won't get it. Why? It will not make sense if you read all of it. But let us try to make sense of it. Okay. What it is saying is that if we have a linear combination of vector v, a1, v1, up to a and vn. So this is a linear combination here. These vectors vn, these vectors will be said to be linearly independent. They will be linearly independent if a1, a1 v1, a2 v2 up to a and vn, or I mean this linear combination, the sum of this linear combination is zero only if the a1, a2 up to an all are equal to zero. Okay. So this was just saying that if these individual components become zero, okay, if they become zero, only then will this linear combination be zero. Since we if these will become zero, every term here will become zero, right? So if every term becomes zero, the linear combination would be equal to zero. Simple thing. So if it happens, then these individual vectors, the v1, v2 up to vn, will be linearly independent. Okay. But now, if I am able to find any other value, if I, instead of zero, if I find any other value, like if I find a value -1, which when put here in the place of a1, and I find a value, I put it here to, if I find another value for it that is -n, I guess. I put a random value here, okay? So if now putting any other value, a value other than zero, if even then it becomes zero, it means if the sum of linear combination becomes zero, then these vectors would be linearly dependent. Now with an example, you will get it clear. I was just talking too much here. You'll just understand it when I'll give you an example. So let's move forward. Yeah. So let's just jump into quantum states here. So we express a quantum state like this, right? This is a cat here. If you remember, Shivani taught you about them. Okay, so this is a cat here, and this this psi inside denotes the quantum state. It is also called a state vector of quantum state. Okay, so this quantum state equals alpha multiplied to a state 10 plus beta multiplied to a state 01. So you'll see that it is the linear combination here. Phi state is the linear combination of 10 and 01, right? So according to the definition of linear independence, they should not be zero until this linear combination should not be zero. The sum of 10 and 01 should not be zero until alpha is equals to beta is equals to zero. Until alpha and beta are zero. Is it the case? Let's see. If we try to add 1 and 0, what will happen? Let me just try to add 1, 0. These two vectors, if I'm adding these two vectors, what I get is 1, 1. Don't I? Now, can I find any vector that makes, can I find any scalar that when multiplied to these vectors will bring this 0? Let me try. Let me multiply it by 2. It won't happen. Let me multiply it by -1 actually. That will make more sense. Let us try multiplying it by -1. What will happen? This when I multiply it by -1, this becomes -1. I can ignore it then. I'll put the minus inside. This will become -1, and the answer will be -1, -1 and 1. So simply, we found no vector actually. We found no scalar which when multiplied to these vectors will bring 0. Only if I multiply all of this with 0. Let me do it now. Oh, sorry. Yeah. So let me just multiply both of them with 0. If I multiply them with 0, whole this part, these vectors, these terms become 0, and the answer would be 0, right? So what we saw here was that they were not but we saw that they are linearly independent. Okay, and one thing I said at the start was the concept that they cannot be expressed in terms of one another. But here you will see that I never talked about it, right? I was just going about equals to zero, not equals to zero, and else. So let us just try to express them in terms of one another. Can I can I create 1 0 from 0 1? Let me have 1 0 here. Can I create 0 1 from it? Is there anything I can multiply it to? Is there any scalar I can multiply it to? You won't find it. You can work it out. You can try to work it out. So you won't be able to express. There won't be any term x. You won't be able to express 1 0 as 0 1. Okay, you won't be able to convert 1 0 to 0 1. So thus they are linearly independent. So both of the things, the concept of equating to zero and the concept of not being able to expressed as one another, both are the same things. Both say that they are these vectors are linearly independent. Okay, let's move forward. Let's check linear independence of this one. Now, let me just do what we read. What we read was that we have to add these vectors, right? Let me add them. I'll do 1 0 plus 2 0. So if I add them, what will happen is that although I'll get 3 0 here, right? But can I find a vector? I should get 3 0 simply if I add them. But can I find a vector that makes this sum 0? So a vector that can make this sum 0 is if we make this one as -2. So if I multiply it by -2, this will become -2. What we'll get is -2 0 and plus 2 0. Isn't this linear combination now equal to 0? It is, right? So these are not so since they are equal, this is equal to 0. Since we have found a scalar that makes this scalar other than 0 that makes this linear combination equals to 0, I can say that they are linearly dependent. So these two vectors are linearly dependent. And what we can also see is actually just a second. Okay. Yeah. So what I was saying now, the second concept was that they cannot be expressed as one event, but you'll see that they can be, right? If I multiply 1 0 with 2, what will I get? I'll get the second vector. I'll get 2 0 here. Makes sense. So this also proves that they are linearly dependent. So this was the concept of independence and linear dependence. Now what are we gonna study is span. Okay, what is the span now? Suppose we have a vector space V. We have a vector space here V, and there are some vectors written here. If you see clearly, we have W1, W2 up to WR. Okay. So what span says is that if a vector space V consists of all possible linear combinations that can be formed of vector W1 to WR, then these vectors W1 to WR are said to span vector space V. Okay, this was lengthy, so let me just make sense out of it. So suppose we have we have a vector space. Suppose I'm just writing it up W1, W2 up to WR. So we have a set of, let me call it vector span. Let me call it S. Okay, here. So this is a vector space here, right now. And then there is a vector space V which will contain many vectors. Like take V1, V2 up to Vn. Okay. Yeah. So if I had to say, just let me move it down a bit. Yeah. So what was I saying? I was saying, yeah, if I have all these vectors here, V1, V2 up to Vn, if all of them are expressible as linear combination of these vectors, which mean what I mean is that I can express V1 in terms of as linear combination of W1 plus W2 and each is multiplied to a scalar coefficient here. I'm not writing it just to make it quick. It will be bulky for me, right? Okay. So if I can express it as linear combination of these vectors, v1, vn, any vector. Okay, I am taking v1. If v1 is also sorry, if I take this v1 vector here and express it in terms of w1 to w2, w1 plus w2 up to wr as linear combination of these vectors w1 to wr, then this vector space S is set to span, this set of vectors, actually it should be a set of vectors. I just need a space. Okay, so these vectors, W1 to WR, can be are set to span the vector space V. They span the vector space V. Any vector from this vector space V will be representable as a linear combination of these W1 to WR, these vectors. Okay, it will make sense now if I give you this example. We read about vector space R2, right? The two-dimensional vector space. We studied about it. So I also asked you guys to have some to check if you are able to express every two-dimensional vector, every vector that is inside this 2D vector space using these two vectors. Okay, so is it possible? Let us check. Let me pick a random vector. Let it be 13 and 6. Okay, so now can I express it as linear combination of these two? So since we have to use these two, let me write them down. We have 1 0 and we have 0 1. Okay, so we'll have a linear combination looking like this, and there would be some some scalar coefficient that when multiplied to these vectors will give out this vector. Okay, so is there, I can multiply 1 0 to 13 and I can multiply 0 1 to 6. What will become now? If I solve this, what will we get is 13 0 plus 0 6. You get it, right? If I add them now, solving for it further, what will I get is 13 6. Same as that. They are both same, right? So what we proved here is that any random vector, you can pick any other random vector, is expressible in terms of these two vectors. So these two vectors span the vector space R2. Okay, this might have made sense. This is a simple thing. Okay, now comes the concept of basis vectors or bases. What bases are that it is also a set of vectors. It contains vectors. If I have a basis, I'll name it B. It contains vectors. Suppose I take W1 to WR again. Okay, it contains them, comma, comma. I'll write it in a better way. Okay, so this is a set of vectors here. So it will be called the basis of a vector space V if it satisfies these two uh, properties that are listed here. Okay, so a set of vectors that satisfies the following properties, then its elements, these vectors here, are called basis of the vector space V. So what are these properties? Let us study. Okay, the vector space, the vectors of the set, these vectors should be linearly independent. Okay, these should be linearly independent. W1 should not be we should not be able to express W1 as linear combination of any other vector. Okay, W1 or any, we can pick any vector here. It should not be expressible as linear combination of other vectors. Clear? Then comes the second property here, which says that vectors should span space V. These vectors should span space V, which means that every vector from this vector space V should be expressible, and every vector that belongs to the vector space V should be expressible in the terms of W1, W2 as linear combination of W1, W2 up to Wn. Okay, simple thing. Now, what a basis basically is, it is just a set of minimal vectors. It will contain these would be the minimum number of vectors that can span a vector space. Okay, we right now we just a while ago we talked about this vector space R2, and as a matter of fact, 1 0 and 0 1 are the basis vectors of this R2. They form the basis of a vector space R2. So let me just take it as an example here. So what it said is that the set of minimal, the basis should be the set of minimal vectors that can span vector space V. So 0, 1 and 1, 0 were spanning vector space V, but and it is so it can, wait a minute, right? I should say it like this. It contains two elements here, right? It contains two elements here. So the minimum number of vectors that will span this whole vector space R2, the 2D vector, the two-dimensional vector space, is 2 here. This will make sense in a while when I tell you about this property here, which is written. What it says is that the number of vectors inside this vector space V, inside this basis vector space, would be equal to the dimensions of vector space V. So the dimensions of vector space R2 were 2, okay? It is a two-dimensional space, so it has two dimensions. Okay. Now, if you notice that how many vectors are there inside the basis of the vector space R2? There are two. There is 1, 0 and 0, 1. I said, right, they are the basis of vector space R2. So there, you will see that they are equal to the dimension. The number of these vectors is equal to the dimension of vector space R2. And suppose now we can have a three-dimensional vector space too, right? So if I have R3 here, how will I create its bases? How will I find its bases? Let me try to write them, okay? What can I do is I'll take a 1 here, then a 0. You'll see that this vector contains three dimensions here. It has three dimensions here, right? So it will all the basis will also contain three dimensions actually. The dimensions of all the vectors inside this basis would be equal to the dimension of the vector space. Okay. So now if I take this vector space R3 and write its basis, what I will get is a vector 1 double 0, another vector 1 0 1 sorry 1 0 1 0, and another vector 0 0 1. Okay, it will look like similar, it will look similar to it, right? Here we had two ones, so first we kept the first one 1 and the other one 0, then we kept the first one 0, then other one 1. Okay, similarly what we did it here also. First we kept the first one 1 and all others 0, then we kept the first 0, the middle one 1, and the sorry first sorry first we kept the first one 1 and all other 0, then we kept the second one 1 and all other 0, then we kept the third one 1 and all other 0. So this formed the basis of vector space R3. And if you notice that the number of these vectors is 3, which is same, which is equal to the dimensions of the vector space R3. So this proves the fact that vector space, the basis vectors of a vector space will be equal to the dimensions of the vector V space V. Okay, the number of basis vectors will be equal to dimension V. Okay, let's move forward. Now is the concept of eigenvectors and eigenvalues. I think this was explained a bit, and yeah, it was explained a bit, right? So I'll clear it out, explain it properly. Now, yesterday when we multiplied a matrix to a vector, what we did was we rotated and scaled it. A matrix is used to rotate and scale a vector. Okay, but when we multiply a matrix to an eigenvector, it is a specific vector. The eigenvector is specific to a matrix, right? They cannot be a universal eigenvector. Every eigenvector is specific to a matrix, right? So suppose if I multiply matrix with this eigenvector, what I get is a vector which is not rotated; it is only scaled. Okay, and it is quite what shall I say? It is similar actually to the scalar vector multiplication. If you remember that multiplying a scalar to a vector is scaled that vector, right? But here multiplying a matrix to a vector is also scaling it. So simply this matrix vector multiplication mimics the scalar vector multiplication. Okay, this thing is very useful, and we'll get into it in a while. That why is it useful in quantum mechanics? Okay, let us first see this equation that is put up here. This equation says that if we have a matrix A, this is matrix A, right? We represent matrices with capital letters. So this is matrix A. which when multiplied to a vector v, this vector here is called the eigenvector. This would be the eigenvector. Sorry, this is so hard to write with this pen. Okay, so suppose this would be the eigenvector here, then their multiplication will equal to this lambda here is called the eigenvalue. Okay, it is called the eigenvalue. Yeah, and this vector, same eigenvector v. So now what is this eigenvalue here? The eigenvalue actually is the amount by which this eigenvector is scaled. Okay, like when we multiplied the matrix to this eigenvector, it got scaled, right? So by the amount by which it is scaled, by which its length increased, is called the eigenvalue. Okay, so when we represent it here, what we said is multiplication of a matrix with an eigenvector gives out the eigenvalue multiplied to that eigenvector. So we can ignore the eigenvector from here and here. What you will see is that this lambda here is scalar equivalent to the matrix A, isn't it? It is we can express this A with this vector lambda. So this eigenvalue lambda, this is scalar, and this is a matrix. So we can represent this matrix in terms of this lambda, this scalar lambda here. Okay, there can be many values for lambda for a single matrix, but the thing is that every square matrix, keep notice of it, that it will always have at least one eigenvector eigenvalue pair. So we can always express a square matrix as a scalar eigenvalue. Okay. Now is the concept of now is probability. Actually, I was gonna explain you how to use these vectors and eigenvalues, but today's topic of quantum mechanics, we will cover this thing also. It will be there, so remember it. Okay. Now let us get into probability. What actually is probability, and why are we studying it in quantum mechanics? So, simply probability can be seen while we play games like while we gamble, while we play cards, while we toss a coins. Simplest thing is tossing a coin, right? So we get probability there. But now in quantum mechanics, what happens that the uncertainty principle actually brings some. Okay, we'll study about it too. But if I have to say it in simple terms, what I'll say is that if we have a quantum state phi, it there is always probability, or it exists in a superposition of other of smaller quantum states. Namely, I can write it as state 0, state 1. You'll understand it in a while what it is. We are gonna go through all these things in today's lecture. Okay. So what I did is express this state phi, state psi, as linear combination of vector 0, cat 0 and uh, cat 1, right? Now what happens is that when we measure it, measurement also we'll study. So when we measure it, this phi state becomes equal to any one of this state. After measurement, I'll say that after measurement, the phi becomes equal to 0 or 1, or it can become equal to 1. So what is happening is that it is collapsing into these states, any one of these states. Okay, and which state will it collapse to? It is actually where probability comes. Okay, there are two possible outcomes for this vector for this quantum state to fall in, right? It can become either 0, either 1. Simply like the coin toss. The outcome of the coin toss could either be heads or either be tails. Similarly, this can either be cat 0 or cat 1. Okay, so here now the probability of falling comes here. Now it depends on the probability, how much chance is there of falling how much chance is there of phi becoming 0 and phi becoming 1, and it is determined by this coefficient here, this alpha and beta. We'll study it in a while. Let me just keep it as a surprise, or let me keep your excitement here. Now, but till then we'll move forward. the first concept here is of vector space V. Sorry, of sample space here. So we know what space is. Okay, so I won't get into it, but the sample space here is, it is the space that contains all possible outcomes of an event. So all possible outcomes of an event, what do I mean by it is, suppose we have an event of tossing a coin. So the possible outcomes are heads and tails. Okay, so similar to vectors, we can create a space that contains the possible outcomes. So let me create a space here that contains heads and tails. So this space here will be called the sample space. Okay, this is the sample space. And now you will say that why is it a space? Why is it not a set? Okay, it is a space because we put elements inside it based on the rule that, is it the possible outcome of an event? Is it the possible outcome of the coin toss here? So the event was the coin toss, right? So only we will only put the outcomes of the coin toss inside the sample space. Okay, are there any questions? Okay, sorry to interrupt you, but yeah. Okay, which is okay. Let me just do it. Let me turn off the fan. Is it fine now? Okay, thank you. So outcome of a point. So what I said was that a sample space of any event, a sample space of any event would be containing, or would be a space found by all of its possible outcomes. Like here, the event was coin toss, and the sample space was heads and tails. Okay, the sample space will contain heads and tails since they are the possible outcomes. Okay, let's move forward now. Now are the properties of this sample space, which are simple, basically, which are very simple. It is saying that all elements here should be mutually exclusive. This means that no two of them can occur simultaneously, which is quite true, right? If I toss a coin, I won't get heads and tails simultaneously. Tossing one coin will either give me heads or it will give me tails, right? So this is what it is saying. It is saying that every event inside this sample space should be mutually exclusive. It should not occur simultaneously. Okay, they should not occur simultaneously. Now, collectively exhaustive means that it should contain all possible outcomes of an event. If I was only putting h here, then it won't be the sample space anymore. Okay, so it should contain all possible outcomes that are possible for any event. Okay, so this is what the concept of sample space were. Sorry.
So the break of 5 minutes is over now. Hope you all learned. And now the second half of the session will be taken by Shivani. So the topic for our second half session is quantum mechanics. So Shivani, will you please start?
Yep. Is my screen visible?
Yes, it's visible.
Okay, cool. Thank you. So I hope you all learned a lot from the maths, and when we are going to teach the quantum mechanics part, I hope you can relate those maths concepts over here. So quantum mechanics can be a bit tricky and you have to dump all of your common sense. Okay, so just see what we are going with. So what exactly is quantum mechanics, right? Well, quantum mechanics is the study of physical phenomena at microscopic level. So what are microscopic level and macroscopic level, right? So microscopic level is something that cannot be seen with naked eye. So its range is from 10⁻³ meter till 10⁻⁻10 meter. And macroscopic level is something that we see in our everyday life, be it the chalk or the small particles or whatever the bottle is, something like that. So in quantum computing, we exploit quantum phenomena like superposition, entanglement, and interference to solve some certain complex problem in reasonable time. One of the examples I could give is protein folding and also a simulation of natural processes. So what are bits? So in yesterday's session, I gave an example, right? That a computer only understands the binary system, and and what binary system has, like, it has two base, right? 1 and 0. So when the transistor gives its on, it's 1, and when it's off, it's 0. Here we have represented the number 53 in the binary system. So this one indicates 1, this 0, this second position is 2. And as you go from right hand side to left hand side, it starts increasing by 2 raised to n. So if this is 1, like this is 1, this is 2, this is 4, this is 8, this is 16, 32, and similarly. So now that we know what are bits, we'll get to quantum bits. So the qubits we use in the physical system exhibit the quantum properties. And there are various ways you can you make a qubit out of. Like anything that has quantum properties can be exploited as a qubit. So there are superconducting qubits, diamond envy center, also photons. So this quantum mechanics behavior quantum mechanics can describe how they behave. And qubits are like this, like I gave the previous example of head and tail, right? Let's say in classical computers, head means 1 and tail means 0, right? So in classical computer, only one state exists. So you only get head or tails. But with qubits, it's like a spinning, it's spinning, the coin is spinning, and at the same time it's head and it's tail too. So unless you measure it, you won't know what the beat is. So that is the advantage, and it helps to solve, like it saves a lot of time complexity and space complexity as well. Then what is a two-level system, right? So similar to the binary system, quantum levels also have a two-level system where we have the state 0 and state 1. So qubits are two-level system with basis 0. When, let's say, if the spin is up, it's 0. If the spin is down, it's 1. And quantum systems are discrete. They are not continuous. So let's get to wave function. So wave function is a probability cloud. And what do I mean by this? Well, let's look at this. Let's say this is an atom and this is the orbital, right? So this is an electron and this is its orbit. So the chances of finding the electron is the probability is very good at the center, but as you start moving to the outer side, the probability decreases. So it's basically nothing but if you see that this is the position, let's say this is the position, and this is the like y-axis indicates the probability. So if we start looking at it at its center, the probability of finding the particle is at max. And if we take a look at various examples and orbitals, so we can see that this cloud, right, the highest region that is glowing, there's a maximum chance of finding a particle in that. So wave function does nothing, but it explains what would be the probability of its state, its position, momentum. And if it's going a bit too fast, let me know in the chat. Okay. So quantum mechanics in quantum computing. Okay. So what is the use of all of the system? Like I said before, there is superposition, entanglement, interference. So all of you must know about the Schrodinger's cat equation, right? So what is this Schrodinger's cat experiment? So he proposed that let's take a box and we put a cat in it. We close the box. Now there's a 50% chance that the cat will be alive and a 50% chance that the cat would be dead. But unless we don't open that box, we won't be able to know if the cat is dead or it's alive. So when we measure it, we break that superposition and we know, okay, the cat is dead or the cat is alive, right? So unless you open the box, you won't know what its state. So you're just assuming that it's existing in the state of being alive and being dead at the same time. So this gives a massive advantage for time complexity and also the space complexity. So what are particles and what are waves? Well, particles are discrete. Let's say if you have a rock and you throw it into a lake, right? Your rock is a particle, it's solid and it does not just move, right? But when you throw it into the lake, it creates ripples, right? Those ripples are continuous. And they don't, it's not like you'll see one ring and then it will stop and then there will be another ring, right? It is continuous and it just keeps on going. So waves are continuous, but particles are discrete. They don't start repeating themselves, right? Particles have a well-defined position. So your rock, you can just hold it and you know its shape, right? And you can know, okay, this is like it is defined. But your waves are continuous, and when something is continuous, you cannot just know its position. And when particles collide, they bounce off each other. Like let's say if you have two balls, you bounce them off one another, they bounce off it. Even while playing tennis, your ball hits the racket, but when it hits it, it bounces off, right? That's how we are able to play a lot of games, right? Be it badminton, be it tennis, ping pong, right? So this helps us with this at macroscopic level. And when waves collide, they interfere. Like if you have been to beach, you'll see that waves, right? If they're coming from the same direction, they interact with one another and form a big wave, right? But as they are reaching towards the shore, so it's like they go in opposite direction. So when the waves collide in an opposite direction, it becomes a plane surface, right? The form is, the amplitude is very less, and this is how waves behave, and this is how particles behave. So what is the wave particle duality? Well, if you look at the photoelectric effect, it will help prove the properties of light as a particle. And if you look at the Davis and Sharma experiment, it will show you the properties of light as a wave. And this might not make sense, but just hang on with me. So let's look at this experiment. So this is a light source. Let's say if you have a torch, you turn it on, and you just pass it through this. Okay. And this setup, let me just explain this setup. This is a screen, and this is a double slit. Okay, double slitted sheet. So when you pass your light, when you turn on your light, it starts interfering like waves, right? And it starts forming the pattern. If you notice, when it passes through the slit, it starts forming the pattern where when they are of the same, like if they are coming from the same in the same direction, their amplitude increases. But when they're coming from opposite direction, they just cancel each other out. And if you see, it start forming the interference pattern. So this helps prove that light is a wave. And we know that from this photoelectric effect that light is particle, right? So when you shine a light on a sodium particle, it start ejecting the electrons from the surface. Hence we know, and we also know that light is made up of photons, right? And photons are a particle. Moving on to interference. Like I've said before, interference is nothing but it states that the elementary particles cannot only be in more than one place at a given time through superposition, but that individual particles, such as photon, can cross its own trajectory and interfere with the direction of its path. So that is the formal definition. But like I said before, interference is nothing but when two waves collide and they start forming patterns, be it coherence or decoherence. Then electron interference. Okay, like I gave the example of light before, but now we'll say let's say we have an electron gun and it starts shooting electron. Okay, so we know that electron is a particle, but when we put it through the double slit and we keep on ejecting the electrons, we'll expect that the electron will hit only at one place. Like if it's a particle, it should just be at one place, right? But it starts forming a pattern of interference, which shows that it is also a wave. And that's the wave particle duality of photons and electrons. This is the pattern that you can observe, right? When they're from the same direction and it start increasing its amplitude, and this is the light band and these are the dark bands. So qubits behave like waves. They also have a superposition. They can be in the state of 0 at the same time and 1 at the same time. And qubits can also interfere with one another. Like you have read about the entanglement too, right? So quantum interference lead to quantum speed up, and this is a Bloch sphere, right? We have seen how we represent some vectors and complex numbers in the polar coordinate systems, right? So here are qubits. Let's say if its spin is up, then it's in the state of 0. If its spin is down, it's in the state of 1. In quantum computing, the Bloch sphere is a geometrical representation of a qubit, right? And it's named after the physicist Felix Bloch. And we can represent its the spin and the state of a qubit by using this Bloch sphere easily. And you can see it's a notation, right? The Ket notation and the Brown notation. What is Heisenberg's uncertainty principle? Well, in 1927, German physicist Werner Heisenberg introduced the uncertainty principle. What it does mean is that you cannot say with a very certainty that you know the position of an electron or a quantum particle and say that you know its position and also its momentum at the same time. Like at the same time, you cannot just have you cannot be very, like you cannot be 100% certain, okay, I know its position and I also know its speed. And here x, it just describes the position, p momentum, h is the Planck's constant, and 4 pi is just a constant value that we take. And this is its equation that we use to find the probability. Like what would be the probability of finding momentum, and it could be like 40% of finding its position, 60% of its momentum, and similarly. So what do I mean by this? Let's look at this tennis ball. Okay, so you can see the blur over here, right? So we are not so certain about what its position is, but we definitely know from where it came and where it's going, right? And we can also see its speed. We can calculate its speed because it's moving and it's in the motion, right? So this is how we know its speed, momentum, but we does not know that what its exact position is. But over here, if you see, a ball is just in mid-air, it's not moving at all. We certainly know what its position is, but because there is no blur, or because there is no way to know where it's coming from, where it's going, what is its speed, right? Because it's just there. We don't know by looking at this picture what would be its speed. For that, we have to let it go. And when we let it go, we cannot predict its position with 100% certainty. Moving on to de Broglie wavelength. So, like I said before, each, like quantum mechanics states, right, that each particle is it has this dual property, right? It is also a particle, it is also a wave. So why am I not interfering? Like why do not I have the interference property, or why does not my cat have the interference property, right? Why doesn't it collide with itself or start multiplying itself and all that stuff, right? Well, because our wavelength is so negligible that we cannot catch how we are moving as waves, right? So, or like let's say if I'm a human, like I am a human, and due to the large mass that I have, my wavelength is so negligible, like it could be around any constant into 10 raised to minus 34, right? So it's that less that I do not, like I have a very negligible wavelength. So yeah, so this is the equation where lambda represents the wavelength, h is the Planck's constant, m is mass, v is the velocity. So our mass is so big that our wavelength is so less. But we know that electrons, photons, they have the mass in range of 10 raised to minus 31, minus 27, right, kgs, right? So that's why due to the low mass, we can definitely observe how they, their wave properties as well as the particle properties. So you can find the wavelength of any particle when you know its mass and speed. You can definitely find its wavelength. Moving on to the superposition, like I explained before in the Schrodinger's cat experiment, the cat is in the box and it's dead and alive at the same time, with the 50% probability of being dead, 50% probability of being alive. Sorry. And this allows earth qubits to exist at the same time as in the state of 0 and at the state of 1. And unless we measure it, we don't know what it is. Okay, we can only predict its probability, but that's it. And this allows, because like let's say if we know, like let's say we have a qubit, one qubit, right, and it can exist in two states. And then let's say we have two qubits, then it can exist in four states. And when we go with three, it starts increasing in the 2 raised to n values, right? So this allows to save a lot of space and also time. So what is entanglement? Let's say you and I, like let's say our particles are correlated, okay? And if this is 1, then this would be 0. Or if this isn't, if its spin is in clockwise direction, then this other particle spin would be in anti-clockwise direction. So we still don't know how it works, but quantum entanglement is a physical phenomena that occurs when a group of particles share a special proximity, like they are interacted physically, but they necessarily do not have to be, in the same distance or like very close, right? They could be here or they could be in space or something like that. So they share a common wave function, okay? So when you take that wave function, like I said before, wave function helps a lot to predict what will be the probability of finding its position, its angular momentum, its spin, right? So they share the same function, and that's why if you can predict one particle's position or speed, you'll know what would be the others. And Einstein considers this behavior impossible as it violated the local realism view of causality, and it's referred to as a spooky action at distance, but it's very real. And that this is how we are able to do a lot of operations on a qubit. And also, if you read about it, we were also able to transport a particle to an outer, like into an outer orbit. And if you want, I can link it to the research paper as well. So yeah, Lokesh, you can take over now. Lokesh.
Thank you, Shivani. Now the further session will be taken by Lokesh. So Lokesh. Lokesh.
Yeah, I'm audible. Hello.
Yes, we can hear you.
Okay, so I'm back, guys. Now, this time we are going to study quantum mechanics. Let me just wait a minute. There's some here. Yeah. So, can you see my screen?
Not yet. Okay, now we can
now
see.
you'll be able.
Yep.
Yeah. Okay, so I'll go through the slide that I'm supposed to present. Yeah. So first thing that we are going to study after everything that she has explained, Shivani has explained, let us get into quantum mechanics actually. Okay. Sorry, let us get into quantum computing a little. Okay. So first thing we are going to study is operators in quantum mechanics. Should have been there many mistakes right now. Okay. Yeah. So have it. Ignore the typos there, right? So we are going to study about operators. What are operators? In classical words, we objects have properties like position, energy, momentum. They have, right? You can have, as there was an example of ball. You can know that the ball is at a particular location. It is, if you say it is kept 5 meters from you, then you are specifying its position, aren't you? So any object in classical world has a position. It has energy, and you know it has energy because things can contain thermal energy, could have contain some heat. So they can have energy in them. They can have kinetic energy. They can have potential energy. Similarly, if they are similarly they can have angular momentum. They can have linear momentum. So these are the properties they the objects in classical world contain, and every actually in quantum world everything contains them, but there what comes there is the uncertainty in it. Okay, here these are certain. In the classical world we see things certain. Okay, now these are called the observables. We call them observables. The position, energy, and momentum are called the observables. And why are they called so? Because they can be measured. We can measure them accurately, so they are called the observables. Now, for each observable in classical world, there is a corresponding Hermitian operator in quantum mechanics. And the word Hermitian here is simple. Hermitian operators are complex unitary matrices. Now, yesterday we studied about unitary matrices, right? They need to be their own inverse. Okay, so now if any complex matrix is its own inverse, then we'll say that it is a Hermitian operator. So what I'm gonna show you right now is a table that contains these operators that we take in one. Like, are you able to see this tab? There is a new tab I opened. Are you able to see that?
Yep, we are.
Okay. So this table here. Sorry, just guys. Okay. So what I was gonna teach is about it is that if we have this here it had a table. Yeah, here it is. So this table here shows the observable and the operators of the that we use in quantum mechanics. So for position, we have a observable symbol X, right? So the operator symbol would be with an hat. You can see there is a hat over here, right? So the operators are denoted by the capital letter and then a hat over here. Okay, so there is a corresponding operator here for position. In 1D, here is position is in 3D, so we have position operators. These can be called position operators, right? Then is momentum operator here. Then is kinetic energy operators. There is potential energy operator. Then we can also have say it as there is a total energy operation. Total energy operator. This total energy operator is actually there is a Hamiltonian operator there that we are going to study about. Similar to this, there can be angular momentum operators. There are three are shown here, which actually are just giving angular momentum for every corresponding axis. They around about which any particle can rotate. Okay, can have any angular momentum. So just a second. Now I'm gonna close this tab. Let me just use that. I am just stopping the share of my screen once there was an issue.
Lokesh, I think your screen is not visible to us.
Yeah, I just closed it for a while. No problem. I'm sharing it again. So it would be visible here. So it is right. It is visible here. So what we saw there were some operators. We saw some operators that were position. We had position operator there. We had a position operator there. We had a momentum operator there. We had an angular momentum operator there. We can have energy operators there. Okay, so for every observable that is in the classical world, there is a corresponding Hermitian operator in the quantum world. Okay, now comes the Hamiltonian operator, the first operator, the first and only actually, the only operator that we are going to study here is this Hamiltonian operator. This Hamiltonian operator is used to measure energy observable of the quantum system. Now, energy observable means the classically we can measure energy without any uncertainty, right? But while coming to quantum, what we have to we will face some uncertainty while varying the amount of energy while measuring the energy. So here we cannot measure simply. We will need an operator to measure. Okay, we use an operator. So this operator here is Hamiltonian operator that gives the energy of a quantum state of a quantum system. We denote it here. We denote it with this H and with a hat above it. Okay, and when it is applied to a quantum state denoted by this phi here, then what we get is the energy of this state phi. So if you remember, doesn't it look like this? I actually explained it today too, right? Multiply to this and we get a lambda and a vector. It looks like this, right? We have a matrix here. Here this H is a Hermitian operator, so it is a unitary matrix. And this V is a vector. This quantum state is a vector here. Here is lambda, then here is energy, and there is the same vector here. So this actually is how we talked about it in the eigenvalue eigenvector things, right? In that topic. So actually, you will notice that this lambda here, which is E, so these are the eigenvalues. Sorry, I don't know how to write properly with it. Anything else? This something showed up here. So what this E and this lambda are, these are eigenvalues, right? So yeah, these are eigenvalues. So these both equations are similar actually. So this we are operating we are applying this Hermitian operator on this eigenstate phi, and what we are getting is that a corresponding eigenvalue that this phi can have, this eigen vector can have. So actually, what this is actually postulate of quantum mechanics, which we are going to study in a while. So what it says is that what actually is happening here is that the value, the energies that this quantum state can have will always be the eigenvalue of this operator H. So every energy, or this is actually a universal thing for every operator, that the output, the output value that it will give would be the eigenvalue of that operator. So here, actually, let me explain it simply. Okay, so what we did is that we took operator and just applied it to a quantum state, and what we get was an eigenvalue of this operator of this matrix. Okay. Now, this gives the energy of our quantum system, or quantum state phi. This is giving the energy of our system phi. Now, what we call it Hamiltonian of this is state phi. When we take the Hamiltonian of this state phi, we get the energy out. We get out the energy. We measure the energy using this Hamiltonian operator. Okay. Now, Hamiltonian actually is calculated using the standard energy equation that we use, which actually says that energy of any system is sum of kinetic energy. This part denotes kinetic energy, right? This part is denoting kinetic energy is equal to the energy of any system is equal to kinetic energy plus potential energy. Simple as that, right? Now we can use this equation to derive the Hamiltonian equation. How? Let's see. Okay, this was something here. Yeah, I forgot to tell you that this is where the discreteness comes in. Let me just delete all this annotation. Yeah. So the possible energy states of a quantum system. Quantum system here is this phi that I've written here. So this phi, this eigenvector phi, is the quantum state that we are working on right now. So the energy states of this quantum system can only be eigenvalues of this Hamiltonian operator, which we saw here. So since a matrix contains specific eigenvalues and eigenvector pairs, so there would be some specific numbers there would be some specific eigenvalues for every operator there. So if I go with this case of energy, then there would be some specific states that this energy can take, that this phi can have. Okay, there would be some specific values of this E. So this is where the discreteness in quantum systems come. What do I mean by this is that, see, in this word, in this graphical world, what happens is that we can have continuous energy increase, right? I can, if at one point I have energy one joules, then at the second I can have energy 2 joules, and thereby continuously I can increase it. Okay, but in quantum world there are discrete levels of energy. Okay, it's like we were told like we were explained when we read it. So what was we told? What were we told is that, take an example of slide. The slides in the park. What happens is that you can slide through these slides continuously. Okay, sorry, my drawing is here a bit stupid. So you can just understand that the slides, the slide can be continuously slid on, right? You can just slide over it. There is no gap between. But this is the case of classical systems. But if we have stairs here, if you have stairs, there are different levels you can see. You can only put step on these levels here. You can either put your foot here in this level, or at this level, or at this level. But nowhere in between. There won't be any place to put your foot on, right? So this is what is the case. This is the case of discreteness in quantum system. This happens in quantum system. So if I take the example of energy, then a quantum system, any particle can only take some few energies, is some few energy states. It can either be this energy E1, it can either be this energy E2, but it can contain this energy or this energy, but no energy in between. So this is what discreteness means. There can be specific, there will be specific energy levels, and in between the particle cannot occupy any other energy level. Okay. So let me just move this to. Now I was going to show you that how we calculate the Hamiltonian using the standard equation, energy equation. Just move forward. So Hamiltonian equation that we get, Hamiltonian actually is canonical quantization of classical energy equation. It is a simple thing actually here. What canonical literally means is that we preserve the basic formula, we preserve the basic structure of something. We work on based on some basic structure, right? So quantization means converting something to quantum, creating a quantum counterpart. So so what is this canonical quantization? What does it mean? Is that we quantize. It is just quantizing, creating a quantum counterpart of a classical theory, while trying to preserve its structure as much as possible. So since here we are preserving this structure this classical structure, we are preserving it. We are preserving the standard formula of calculating the energy. What is this formula? It is energy, total energy is equals to Ke plus P. We are going to keep this preserved. Okay. How? Let's see. Now let us try to quantize this energy equation, E is equals to half mv squared plus potential energy. So what I can say is that I can express this kinetic energy here as momentum. I just multiply up here and down here. I will multiply with m. Both the denominator and the numerator will be multiplied by m. So what will I get is m by m multiplied to half mv square. Let me of distance x. How much
Lokesh, we
like
lost
I
you
can
for
have
a second.
like
Could you
gravitational
just
potential,
repeat?
right? Yeah. Which part?
Last last few seconds.
The quantization, the canonical quantization.
Yeah, after that, when you started with the energy equation.
Okay. I'll do it again. Wait a minute. Yeah. So what I was just saying is that I am going to express. I am going to quantize this equation right now. So I am going to express this kinetic energy part as in terms of momentum. Okay. How will I do it? I'll do it separately now. So I have half mv square here. What I can do is I can multiply it by m upon m. I can multiply it, like, right? So when I do it, what will I get is half m square v square. Well, it is this m square v square simply is mv square whole square, right? Mv whole square, or mv whole square, right? And there, what will come here is m in the denominator, right? So this is the expression of this mv square whole square is actually just momentum squared. You notice it is, right. So what I did is I expressed kinetic energy in terms of momentum. Now I'm going to use it here. I'll do p square by 2m plus. Now comes the potential energy part. So I'll write potential energy with v, which is here a function of x, which means that the potential energy depends on the distance. It's like the gravitational potential, the gravitational potential energy, depends on the distance from the ground, right? It is what it depends on. So I expressed the potential energy as V, in which is dependent on the term x, the distance. Okay. Now, what can I do? Let us see. Okay, there is a hodgepodge here, whole lot of hodgepodge. So I'm just gonna erase it. You will understand what I've written. So the momentum calculated, now here the momentum, we heard about we read about sorry, momentum calculus, momentum operator in a while, right? There was a momentum operator, right? So this momentum can be found out, we can find it out using the momentum operator, right? So I'll replace this momentum with momentum operator, and the distance can be found out. We can find it out using the quantum position operator, which is like this. Okay. So this Hamiltonian now becomes P, which is now I'm going to use. Sorry, I have already written it, I guess. So let me just not write it again. Yeah. So the energy equation becomes this. The energy equation becomes Hamiltonian equals to the momentum operator squared upon 2m plus v and the x operator, position operator. Okay. So this is what we did. We just calculated the Hamiltonian using the classical energy equation. Okay. Great. Now this is an interesting topic of measurement. Before it, I'll tell you something. What Why do we measure, and what is the need of measurement actually? So before you studied about the superposition, right? So a state actually, phi state is not just a single state. It is just it is the linear combination of various states. And right now, although I can only denote here, if I'm denoting it with 0 and 1, they can be infinite states. I am doing it because we are using a two-level system. Okay, I'm using two states here, two possible states here. Okay, let me explain it a little bit more. So what I'm doing here is that let me just express this phi, this quantum state, as alpha, beta, ket 1. So what I did is I expressed it as the linear combination of two possible states. So it can, when I measure it, after a while, it can become either 0, cat 0, either cat 1. This is something that I mentioned in the probability part also while starting. So what I'm going to use it now is that, see, the phi is the quantum state of a qubit, right? And a qubit basically is a two-level systems, which means that it can only attain two values, two possible values, which it did here. It was 0 and 1. It can only attain these two values. So, although in reality, if we take a particle, its quantum state can actually have infinite possible possible states that it can fall in. So this is called superposition. This being as in this state phi is actually in superposition of being into any of these two states. So until we measure it, it maintains this superposition, this linear combination. It maintains it. But when we measure, what happens is that the phi either becomes 0 or it becomes 1. Okay, you understood it with the what shall I say, the cat experiment, the Schrodinger's cat experiment. So you can just analogously you can understand it here, right? So now, what is this concept of measurement? Measurement is the process of measuring the state of a quantum system. We measure it. We try to find out what is this going to be. Is it going to be 0 or 1? Because right now it is not 0, neither it is 1. It is the superposition of both, right? So, and this here slide is actually properly showing what am I saying. Okay, I'll refer to it later. Just let me get through the definitions. Okay, so the act of measuring it, the act of finding out what state this system is in, is called the measurement. And what we do is that when we measure, it does not remain in the superposition. Instead, it collapses to either one of the states. It will become one of the state. It will either the five. Sorry, I'll write it here. So either the phi will become 0 or either the phi will become 1. Sorry, it is psi. I'm just messing up with the numbers. So sorry, the words. So now let's move forward. So we can measure anything like, right? We can measure anything like energy, position, momentum using the operators we talked about. So what we do actually is that first we apply that operator to our quantum state. We apply this like we applied the Hamiltonian operator to our state, and what we get is then we measure it. What we get after the measurement, what we get is the energy output. This is what we were getting in just a few slides back, right? So this is what measurement was. So we can measure anything like energy, position, and momentum. Okay. Now, upon measurement, what happens is the superposition of the quantum states collapses to one of the states in the superposition. So this here is collapsing. It is collapsing to either one of the states. It will become either one of the states. And now the probability is, now you will think that which one of the state will it collapse to? Which one will it become? This depends on these coefficients here, this phi and beta that I read, sorry, this alpha and beta that I wrote here. It depends on this. Okay, the probability of measuring a measuring a qubit state is probability amplitude squared of that state. Now, these alpha and beta are called probability amplitudes. They give you probability of something, and I guess if we will be having time, I will explain why we use probability amplitudes here. But let's get on with it. Let's bear with it right now. So these are called the probability amplitudes. Now the probability, how we find the probability of it? When we have to find the probability of falling, or that this phi will collapse into any one of these states. What we do is we take the square of alpha of this, what shall I say, this probability amplitude, and we square it. So this would be the probability of falling into the state 0. Or I should write it properly. I should write it a bit mathematically. So what will I write is that the probability of state cat 0 is actually just alpha squared. Probability of falling into state 1 is just beta squared. This is given by the Bond's rule, and it is a let me write it. And yeah, it is a probability. Sorry, it is a postulate of quantum mechanics. We are going to go through it in a while. Okay. Now, this is how it pictorial representation here is. Quantum state when measured, this here is shows the measurement, and you will see it a lot when you go through the quiz, go through IBM Composer and Qiskit. Okay, it is shown there very much. So this is actually denoting measurement, and what happens is that this qubit falls into classical bits. You will understand this thing. You will understand it by today's end, I guess. Let's just go with it right now. Okay, so where was I? Yeah. So this one I told you about the bond rule. Now is this Stern-Gerlach experiment? Very interesting thing. One of the favorite things I like. Okay. So what Stern-Gerlach experiment is that? In order to know that electron spin is two-level system, Stern-Gerlach experiment is performed. Okay, so it tells us that it proves that yeah, electrons spin is a two-level system. Now you would be thinking that what is electron spin? So it is an inherent property of every quantum particle that it has some angular momentum. Okay, if this was an electron, then it would be having an angular momentum, right? It has an angular momentum. Now, what is that? This angular momentum, this property is called spin. But spin is said to be either up. It can either be up or it can either be down. Okay, it can either be up or it can either be down. Now, how are we calling it up and down is based on the right hand rule. Do you guys remember what right hand rule is? What you do is just take your right hand, you curl the fingers towards your palm, and then your thumb is pointing upwards, right? So now what you do is you try to curl the fingers in the direction of the angular momentum, in the direction of which the angular momentum is. So right here you will see that it is anti-clockwise direction. So your thumb will point upwards, wouldn't it? So we will call it up spin, spin up. Now similarly, we can have a spin down when this system is rotate. It has an angular momentum directed towards clockwise. Now, if you try to measure, if you try to use the right hand rule, you will see that if you curl your fingers towards the direction, you will find that your thumb now points downwards. So this is given by the right hand rule. Okay. Now what we do is we see here that we have defined this spin for only two values. It can either have up and down. So it is a two-level system, right? But how did we prove it? This Stern-Gerlach experiment proves that spin is a is a two-level system. Now, what Stern-Gerlach experiment is actually? First of all, what we do, let us perform something. Let us perform this Stern-Gerlach experiment with magnets. What we do here is we take two magnets, and there's something about their shapes. I'll go into it in a while, but you are not going to. Okay, it is not visible here, so I'll go through it in the next slides. So what we do here is we take two magnets. Here is a magnet. Sorry, here we take two magnets and orient them and arrange them in this way. I have kept the North Pole down and the South Pole up. You can have any. Okay. Okay. So now the magnetic field inside would be upwards. Okay. Now, if I have another magnet, if I pass a magnet kept vertical, this magnet is kept, its orientation is vertical, it is upwards. Okay, it is similar to, okay, it is upwards, right? Now, if I pass this magnet through these two magnets, what will happen? Since it is north and south here, it will just pass through, the north will be attracted to the south to, and it will pass unchanged. And in a while, what will happen? It would reach here and we'll have the magnet same oriented vertically. So we started with a vertical here, and what we then got is a vertical again. Here the magnet's orientation, actually I'm talking about orientation. We started from vertical orientation, it was vertical orientation right here. Simple. Now let us do it. Yeah, now let us do it horizontally. Suppose now I have kept the magnet horizontally, and this upper here is north and this is south. And actually in the previous one, you can invert the magnet's orientation. You can put it down here. And what will happen is that the south pole will since the south pole will repel the south pole, and the north pole will repel the north pole, and it will again, or it will after passing through, what we'll get is only the, let me just show it here. Yeah, so if I just take south here instead of north and put a north here, what will happen while passing through? The north would be repelled by it and the south would be repelled by this south. Okay, so it will rotate here and again arrange itself according to the magnetic field, which is from north to south, right? And again, what we will get is the same output. The magnet would be arranged vertically with north and south. Okay, got it? Now what we shall do is that we are perform now we'll perform the with vertical, or sorry, horizontal orientation. It is kept horizontal here. Okay, so now let me pass it through. You know what we are going to do. What will happen? The north will okay. Let me just do it. And yeah, there is some problem here because I just kept the magnets vertical, but instead they should have been horizontal. So I'll just draw another one. So suppose this is the wall here. This is the wall here. Now I am having a magnet here. Yeah. Pardon me for this stupid drawing, but bear it. Bear it. So I'm having now two magnets here arranged vertically, sorry, horizontally, N and S. Now, what if I put a magnet here? What if I put a magnet here with north and south? So what will happen is that, okay, I'll take it as south and it as north. What will happen that it will again pass through unchanged. It will simply again be like this at the end. What we'll get is south and north here. You see, this is what happens in the case of magnets. But since now magnets, since every electrons do have their magnetic charge, right? They can also behave as magnets. So let us do it with these. Now, before going through it, just go look at this image here. There is a unique shape. You can observe it is the unique shape of magnets, right? It is like this here, and it has a cone up here. So this is made so that when we pass the electrons through it, the magnetic field is always perpendicular to them. Okay, it is always perpendicular to them. So this is the reason of this weird shape, nothing much. And what we are actually doing here is that this is an electron ejector. It is the source. It is emitter. So it is emitting the electrons here. They are being directed through this the arrangement through the apparatus of this Stern-Gallard experiment. And finally, what we get, we'll study what we'll get. Okay. So let me just clean it out. Yeah. Now, what we do is let us measure this. Let us measure these all this in the x-axis. I am taking this as x-axis. This is sorry z-axis. This is plus z-axis. This goes here minus z-axis, right? So this is our wall. This is our wall. And now again, I have two magnets kept here in the vertical because see, it is similar to the vertical orientation that I showed you, right? Measuring through the z-axis is similar to the vertical orientation. Now I had it here. Now I am writing north up, and I have south here. Okay. Now there be some bunch of electrons that I have to pass through these magnets. But okay, one more thing. Okay, no, let me just continue with it. Now, if I pass them through, what should we observe? You will think that based on their observation, based on their, at this point right now, they can have random spins. Okay, they can be in they are in superposition of spins actually. So they can be in superposition of various spins, various angular momentums. Now, when I pass through them, what will happen is that they will arrange themselves based on this magnetic field. These electrons will arrange themselves depending on the direction of the magnetic field. Okay. Now, now when I pass them through, what happens is that a weird thing is observed. Half of the electrons go up, half of the electrons go down. Why are they being deviated? It is because these electrons actually have charge, right? So we have an equation of force applied. Force we have an equation of force which is equals to QVB when kept in a magnetic field. Okay, this is an equation. So whenever since electrons have charge, there is a charge here. This Q is charge, right? So whenever a charged particle is passed through a magnetic field, it experiences a force and it deviates. Okay, experiences a magnetic force. So since electrons have charge, so they will deviate here, right? So when we pass through it, they arrange themselves based on the magnetic field. But what can be their arrangement actually, right? What can be their arrangement? Either they will either take up spin up, or they will either take up spin down. Okay. Now, if they are spin up, then they will go through one. They will experience force on one direction, and if they are spin down, they will experience force on the opposite direction. So half of the electrons go down here, they go down here, and half of the electrons go up here. So what does this prove? Is that like see in magnets what happened was that we yeah let me remove it here. In magnets what we saw was that depending on the angle, depending on the orientation, we got the output. Suppose now if I am was seeing the screen at which I threw the magnets, right, and these are the north and south magnet that I kept. And if I throw a magnet from here, from my towards the this wall, if I throw them, so if I throw it a magnet vertically, I'll get it vertical. If I throw it horizontally, I'll get it horizontal. If I throw it at an angle, I'll get it in an angle. There won't be a change. They will arrange it themselves like this. But I'll get a pattern like this, looking like this, right? I will get a pattern looking like this. You can contemplate it. Now, but when I do the same with these electrons, what am I getting? Okay, I have put it right here. It can be the magnet would be here too. They can be here too because yeah, they can be here too, right? So if I put the magnets here and the magnet here, and I throw electrons towards the wall, what will I get? The electrons, what do? They do is they start arranging themselves like this. They move one, some half of the electrons go up here, half of the electrons go down here. So isn't it weird, right? We are not getting any pattern here. This actually, what does it show is that, wait a minute. What it shows is that electron spin is a two level system. It can only attain two states, right? Because the orientation here is here we changed orientation, right? When we change the orientation, we got some different orientation. Output were many orientations. There were this is up, there was one up, there is one down, there is one horizontal, there is one at an there are two at angles. So there were a possible number of outcomes of orientation, right? Now, but in electrons case, here they can have any random spin. They can have spin at this direction. They can have spin like this. They can have spin like this. But after going here, what happened is that their spin was either zero. After passing through it, they aligned themselves through either up or either down. Okay, randomly they did it. Okay, so that's why we get then they experience the force and they moved either to upward direction or either to the downward direction. Okay, so since instead of getting an arrangement of outcomes like here, we only had two outcomes, either up or either down. So this proves that it is a two-level system since possible states of collaboration. See here it was phi actually, right? It is a wave function which is in superposition of random spins. But after the measurement, this here we performed a measurement. After the measurement, what we get is either up state or either down state. Okay, so which prove there are only two output states, so which proves that this spin is a two-level system. Simple as that. This was measurement in z-axis. Similarly, we can measure in the x-axis too. Okay, so what would be the measurement in x-axis? Sorry, let me just brief it quickly. It would be simply having a screen here again similar to that. We will orient the magnets like this. Okay, yeah. We will orient the magnets like this. This is north, I guess. This is south, and we'll keep them here. Right? Now, if I throw the bunch of electrons similarly, if I throw it here, what will I get? Now, see, the force would apply would be either in this direction or either in that direction. Okay, so half of the electrons will go to this direction, half will go through this direction. Now we will observe a bunch in this direction and another bunch in this direction. So I consider this as negative x-axis. This is positive x-axis. Yeah, if there is any question regarding this, because I like this topic and also it is a very important topic. So if there is any question, you can just post it right now. Shall I? Hey, am I audible? Can I get a response? Am I audible? Is there any problem? Guess there's a problem. Okay, great, great. Thank you. I thought there was some problem. So postulates of now the postulates of quantum mechanics. We are totally into the quantum mechanics. The first postulate here is about the wave function. We can call it a wave function postulate. Let me just open some pages because actually they will help me training it. Pardon me if you don't judge me by it. Okay. So yeah. So the state of a quantum mechanical system is completely defined by the wave function phi. The first postulate says that we can define any quantum state as a wave function phi. What does it mean? Because we already this phi here we already use an example to describe a quantum state that was in superposition of other states. We use we used this as an example, right? So the the quantum state of this quantum mechanical system was was described using this phi here. Okay, so this is the postulate that says that not just this, but we can have any quantum system explained by, we can have this state of any quantum system defined by this phi. This is called the wave function. We have a wave function here. This describes all the properties. This wave function describes all the properties of any quantum system. Like it will have the knowledge of position. It will have the knowledge of energy. It will have that of spin. It will have knowledge of the momentum. Okay, and when we measure it, it collapses. This wave function collapses based on a measurement, based on the thing we are going to measure. Like when we measured with using the Hamiltonian operator, this wave function actually collapsed into the energy, right? That energy was the information about that energy was already inside this wave function. Okay, before measuring it, this wave function was in a superposition of various energy states. But when we measured this wave function, just collapsed. When we applied the Hamiltonian, this wave function just collapsed to one energy. Let me just write it again. It will be easier. So what it did was it collapsed, right? It collapsed into one energy state, right? And this energy state is actually the eigenvalue of this Hamiltonian operator. Okay, this was already told. There is nothing more, and this actually is the another postulate. So let me just go through it. Second one says that every observable like energy, momentum, and else in the classical mechanics in the classical world, it is a corresponding Hermitian operator. You know what Hermitian operators are? Unitary complex matrices, right? Uh, for any observable, there is a Hermitian operator denoted by A and with an hat. It is a general representation. This can be H here, this can be P here, this can be anything. Okay. Okay. Now what can we do is this quantum mechanics when this operator acts on this state phi. Okay. This there is a Okay, let me just, in simple words, observable is any observable in classical mechanics has a corresponding Hermitian operator A in quantum mechanics that acts on this wave function psi. Please, I am messing up with psi and phi, so just ignore it, get it correct yourself, right? Sorry for that. Now it acts on this is the wave function phi. The result of an operator A can only be the eigenvalues of the operator A. We saw it here, right? We saw it. This was the matrix. This was the Hermitian operator that we applied on this state, and this state collapsed to any one of this to an eigenvalue of this operator. So this is what the third postulate shows. Actually, we can name these postulates by two. I can call the first one as wave function postulate, right? And I can call the second one as operator postulate. Wait a minute. I had okay. Let's just leave it. I'll tell you them later. So this was the first postulate, second and the third postulate, and we move to fourth postulate. The fourth postulate, what does it say? Is that the probability of measuring a state phi with an operator A is the square of inner product of phi with the corresponding eigenvector. Now this is really a lot that to read, and you would be confused about it. So this, okay, this one is called the probability postulate. So this here is the probability postulate. It tells the probability of any corresponding of the, it tells the probability of any quantum state to fall into a certain eigen state, right? To fall into a certain eigen value. Okay, let me just tell you what it is saying. Let us have a quantum state phi again, sorry, psi again, and then let us have a operator A. Okay, if I had to explain you about this, yeah. So let me just, okay, one thing I forgot to mention. I'm just sorry, I'm just jumbling up. So let me start again a little. So I can represent this mathematically, right? In a proper way. You will, if I represent it, what would it be? So probability of falling, of this probability of measuring the state phi with an operator A, okay, is the square of the probability. Let me call this thing as A, okay. The probability of measuring it would be equal to, this A here is actually the eigenvalue of operator A. It is it is eigenvalue. Let me say it AI, because there can be many eigenvalues for this operator A. So probability that after measurement, what we get is a certain eigenvector AI is actually the inner product, the sorry, the square of the modulus of inner product of a I with the state phi. Okay, so how this inner product thing, what I wrote here is actually, you can see here it, you can see it like this. This AI is represented as bra here, and it is represented, the phi is represented as cat. So what we are doing is we are multiplying a row vector AI. Sorry, we are. Oh, sorry, I just said something wrong here. This is not the eigenvalue. This is eigenvector. Sorry, this AI was the eigenvector actually that it can fall into, because okay, this will create confusion if I don't explain. So here, what was happening is that any state that on which we apply an operator, this state is actually an eigenvector, right? Oops, I'm confused now. I'm confused how to tell you this thing. So what shall I just? I should just say is that, yeah. This here is an eigenstate here. So when I express this phi here as 0 and plus 1 here. So these here are the eigenstates also. Okay, these are here. These here are the eigenstates. And when I apply an operator on A, when I apply an operator here, so what happens is that I apply this. Yeah, this thing was something I should have told you that I forgot to, that how we apply an operator on quantum state like this, right? So how do we do it? We can learn it here. What we do is we take this operator and apply to each of the state in the superposition. What I'll do is that I'll apply A to this A operator to this phi alpha, and I'll apply it to the phi, and yeah, I'll apply to the this operator to the alpha. Sorry, what am I saying? I applied this A to alpha cat 0, and then I applied this A to beta cat 1. Okay, so this is basically, you will see that it is simply it is like distributive property, right? I have distributed this A to both of them. While doing it, it was actually like this, right? So I distributed this operator to both of them, didn't I? Now, what we'll get is that if I have to find the probability of measuring it, what I'll get is that I will take the alpha here out, and then I'll apply this operator A. Wait a minute. Just erase it again. Oh. Yeah, so measure when I'll do a measurement by applying this operator here, what will I get? Is that suppose I am measuring it. Okay, we have not studied the matrices, right? Gates and else. Okay, when we see them, we'll understand it, right? Measurement of, I'm a bit confused about how to explain this thing to you. What I do is, so this is state, yeah. When I applied it, so if I have to find what is the probability of getting this state, getting the state 0. Here's what I do is that I take phi here, probability of 0 here. What is the probability of falling into the state 0 here, right? When I apply this operator A. So what I do is that this actually I have written here 0, but this is where the confusion occurred to me too. It should have been instead of writing it as a wait a minute, I'll just move this thing down a bit. Yeah, instead of writing it as cat 0, cat 1, I can also write it. If you see, I can write it as a I sorry a1. I can write it as a2, and I can extend it up to an. So since I have got what I was going wrong, I can write it again. Okay, I'll just make this thing quite clear to you. So yeah, what I was saying now is that suppose we have a state phi, and now I am representing it in terms of alpha, or let me just change, instead of writing alpha, let me just use c here. This c is a constant, this c is a scalar actually, that this is which can be complex. This is the probability and amplitude that which is similar to the alpha and beta we saw earlier, right? So I can write it as C, and which it is in the superposition of state A1 plus, sorry, C1 here, C2, A2 up to, I can take it to Cn, A, sorry, CIAI. Let me just take it CIAI because it is what we have written here, right? So this phi state is, you'll see it is a linear combination, right? We studied it. So this is a vector, this is a scalar. So I represented it, this state as linear combination here. Now, so if I was to find when I operate, when I measure it, when I apply an operator A here, what will I get? I apply an operator A here to this state. So I'll apply it to, what will happen is that I'll apply this individually to each of these states. I'll do it to A, sorry, A C1, AI, this up to operator A, applied to state C, I, AI. Okay. This is what I was saying. Hope it is clear right now. This is much part. Now, what I'm going to do is I'm willing to find the probability of having a certain state here, right? So what I do is I take the inner product of this phi, the phi out here. I take this inner product of phi with every single with the state I want to find out actually about. What I'm trying to say is that I want to find out that what is the probability that this alpha here, this phi here will will collapse to the state AI, or sorry, A1, or it will collapse. What is the probability that it will collapse into the state A2? So to find this, what we do is that we simply take the inner product of the corresponding eigenstate I'm talking about. Okay, so these eigenstates here, these AI and AI, all these are the eigenstate vectors of this matrix A, this operator A. They will only be the eigenstates of this vector, this operator A. Remember this thing, right? So what do we do now is to find the probability. The probability that it will fall into A1, it will fall into A1 after measurement, it collapses to A1. What will this probability become? This probability will just be the modulus squared, this modulus squared of inner product of the AI is the A1 here. We are talking about A1, right? So we just take inner product of it of A1 with the phi. Simple. So we just took the inner product of A1 with phi. So this, and we squared it. We took the modulus and we squared it. So this gives the probability of finding this A in the in what shall I say? Finding this wave function collapsed to this state A1. Simple, understood? So this is what it said. Now, in this case, what is this probability actually? What this probability will be? This probability actually is this coefficient here inside this inner product here is the coefficient. This becomes the coefficient C1, and it is the square of it. Okay, so this is how we find the probability. Now, if there are any questions, because this got a little confusing, so if there are any questions, you can ask me. Okay, I'm looking at the chat here. If there are, so ask me. I'm waiting 10 seconds more, then I'll move on. Okay, voice. Actually, I can now. Is it fine? Am I audible now?
Yes.
Great. So I'll just move on now. So now the fifth, actually going forward, the fifth postulate here is that the wave function evolves in time according to the time-dependent Schrodinger equation. Okay, this is something that we guys all wait a lot about, right? Yeah, we'll get to study the Schrodinger's equation. So this is here it is, and yeah, one more thing. This here, this C1 actually is the eigenvalue. This is the eigenvalue of the operator A. Okay, these are the possible eigenvalues of the operator A. Don't just panic about it. No, I should not just say like this. I will move forward with fifth right now. These things will get more confused otherwise. So the wave function evolves. What is this evolution? What does evolution means? Is that if you just keep a particle anywhere, it will change, right? Nothing is constant. Change except change. Change is constant. So the particle too changes. Its wave function changes. Its position changes after some time. You start up, you shoot a photon, and after some time, after 1 second, it is 3 into 10 to the power 8 meters away from you. So its position changed, right? So this actually, all these things can be, this evolution of wave function can be defined using this time-dependent Schrodinger's equation. And actually, what it is doing is that you can notice here is the Hermitian operator here. You can see a Hermitian operator, sorry, Hamiltonian operator being used here on the state psi here, which is a function of R. R here was, it is the position. It is position in 3 dimensions. R is position in X and X, Y, and Z axes. It is the position in 3 dimensions, which is equal, and time. It is time dependent, and it also takes care of the time, right? So what is this saying? That it is this phi here depends on the position and time. Its position actually is depending on time, we can say. Now it is equal to the iota here. See, we studied complex numbers, right? And we might have been confused that why are they showing up? They are in the basic, they are in the principle, they are in the fundamental equations of quantum mechanics. In this Schrodinger's equation, I shows up itself. Now, this h here is the reduced Planck constant. I guess its value is h upon, sorry, h upon 2 pi. Am I wrong? Am I wrong? If I am wrong, can anybody correct me? I guess I'm not. Then I have no response. So what it does is it shows here we are what we see is a differentiation here. What it shows means here is the it shows the change of phi d phi. It shows d phi by dt. How much does phi changes with t? Simple. This was our Schrödinger's equation, and what it did here was it told us about the position in x, y, z axes in 3 dimensions. This showed the position in. Sorry, this actually showed energy. I'm sorry. This showed energy after some time. After some time was spent. Okay, so this was the time dependent Schrödinger's equation. I got a bit confused and I messed up again. No problem. So what the last postulate here we have is the total wave function must be antisymmetric with respect to the interchange of all coordinates of one fermion to go with those of others, which actually written here is quite tough. So I just use a simple terminology, right? So what I can say is quantum states generally evolve with time. This also reverses the normalization of the state, the time evolution. Okay, what it is saying is that the operator, the evolution, this evolution of wave function we did is reversible actually. Okay, it actually is reversible. Ignore this, whatever here it was written, it is a complex definition. I'm going with a simpler one. So what it shows that if we apply an operator, let me just have an operator U, which shows the evolution of time, which is actually showing the evolution of time, evolution of this quantum state with time. This evolves the quantum state with time. Now, what the thing is that if I again apply this unitary operator here, sorry, this U here, and on this operation, this quantum state here again, if I apply it, yeah. So what will happen is that see, since it is a unitary operator, it would be its own it would be its own inverse, right? So if I apply it here, so what will happen? We are multiplying the operator u with itself. So since they are in both each other's inverses, they are u is the inverse of itself. So this will give 1, wouldn't it? Won't it? And yeah, it will give. And what we are left about is state phi again. So we started with state phi. If we applied a unitary operator here, and it let it evolve in time. It evolved in time for time t. So let me just instead of doing this, let me just call it ut. It is time dependent operator. It is changing the wave function with time. Okay, so I just mentioned ut here. So now, after some time, when this had evolved, after some time, we try to reverse it. What we did is we applied the same operator again. Okay. Now applying the same operator again, reversed it, and it actually cancelled out the effect of the first operation. How showed it mathematically. And again, what we got was the initial wave function that we started with. We got the initial wave function, right? So this is what our sixth postulate tells about. There's nothing much in it. It is also saying that it is norm preserving. Norm actually is just the magnitude, right? The magnitude of anything is also referred to as norm. So this magnitude, so simple thing, and leave it. Don't go deeply into it. Okay. Now we can also say that this ut, this operator u here, ut, this time dependent, is same as operator u minus t, which is reversing the time. It is taking time forward, it is taking time reverse. But what we are actually doing is that applying the same operator u again. Okay. Okay. This was this was all about our, what shall I say? Yeah, this was all about our postulates. Now is encoding information on a qubit. How do we encode information on a qubit? What we do actually is, what does encoding information basically means? Now we are into a little into quantum computing. So since in a classical bits, how do we encode information? Suppose I had to write my name, and my name, so my name is Lokesh, and I can write it by encoding this into bits. Suppose it is not truly this what I'm going to write, but suppose it is 1001110. Okay, suppose this represents location. Okay, there is a zero extra. Let me just move. So 100111 represents my name location. So what we did is that we encoded this information into these bits, right? We can change their state from we made them either 1 or either 0 and encoded this information here too. Here. Now similar things we can do with qubit. But how we do all this is by applying gates. Okay, what we do is we apply gates to these qubits to the initially every qubit in this is in the state 0, this cat 0. Now where does this state 0 and s come from? So I told you that the qubits are two level systems, so we just named one state as cat 1 and we named the other state as cat 0. Okay, and the cat is here because these states actually are vectors. They are vectors. Okay, they are not scalars. So we represent them as cat. And cat is simply the column vector. So a little revision here. Now, what happens is that initially when we start with the qubit, it is in a 0 state. Now, what we do is we apply a certain gate on it. Let me represent this gate with ZU. This gate can be also said as an operator. It can also be we can call it an operator too. But what we do is we apply a gate to this state and change its state, similar to what the operators do. Okay. Now, what we do is we change the state and then we measure it. We perform measurement on it. And measurement, as I said initially in the slide we talked measurement about, it is denoted by this thing here, this meter sign here, right? Now this will give me some certain state. This the phi actually. This let me just write phi here. Phi starting phi was 0. Then we applied a u here. Then we measured it. Then we applied a gate actually here, and we measured it. And now the phi would have fallen into some state. Now there would be some state. It would not be 0 here if we applied a gate. And now what state would it be? This state will be an eigenvector. It would be an eigenstate or eigenvector of this gate that we applied, this matrix or this operator we applied here. So why is it so? It is because of this. Where is it? Yeah, it is actually because of this postulate here. Or was this another postulate? No. So this postulate, the fourth postulate, says it. See, it shows us that it can only fall. This A1 and this A1 is actually the eigenstate of the. It is the eigenstate of the matrix A, the operator A. So according to the fourth postulate here also, the resulting state would be an eigenvector of this operator we applied here. So let me just name it as UI. Okay, simple thing that I wanted to tell you. So this was how we do what we do with gates. Now let us study some gates. So it would be great if we study some gates, right? Or I think I should give some break. I need while I am tired now. So let us have 5 minutes break again if everybody agrees on it.
Yep, we can take a break for 5 minutes. So guys, stay tuned and like come back after 5 minutes. Yeah, so I just said that take a break for 5 minutes and come back again.
Okay, Arvind, you were asking for repeating something. What was it? Can you type that in chat? Okay, encoding info, right? Okay, let me just tell you this. So encoding information, what I meant is that, see, what actually encoding means is we are manipulating a bit, right? Here too, we are manipulating a bit. we are changing its state. We are either making it 1 or either making it 0. Similarly, we manipulate the qubit also. But instead of 1001, what we have here is, instead of bits, we have qubits, which are actually vectors. They are vectors, right? They are vector states. So what we do is we manipulate them using the gates. You see, in classical world, if you know how we initially suppose the bit was 0, how do I manipulate it and make it 1? I apply the NOT gate, right? Sorry, the NOT gate is not written like this. Let me just do. So what I apply is I apply a NOT gate. It is a NOT gate, I guess. So it makes it 1, right? Similarly, we apply gates in quantum mechanics too. Okay, and but since you know that there is a concept of measurement here, the after just applying the gate, what happens is that the state changes from 0 to 1. But these gates actually preserve the quantum superposition. This is a very important thing I forgot to mention. They preserve the superposition of the state. Now, after applying anything on this phi, after applying this gate on this phi, what will happen is that it will again be in a superposition, but now after superposition, it would be in a superposition of the eigenvectors of u. That makes sense, because see, after a while it has to fall, it has to collapse into one of the eigenvectors of v, right? The postulate told us. So before before collapsing, before measurement also, after we apply the u, the phi would be in a superposition of the of quantum state of the eigenvectors of u, right? I can write it similar as I mentioned before. I can write it as c1 up to up to ci ui. Okay, if this makes sense, I guess you got it. Just if not, you can go through it later. You'll understand it. And now, why are we measuring? Is because similar. Now we cannot have a superposition as our information, right? We don't. There is no certainty here. So to have a certainty, we have to measure. We collapse the wave function. We apply measurement here, and measurement actually is similar to this Stern-Gerlach experiment we did, right? I told you already. So that was measurement. And then something I was gonna tell, but since I've already started, let's just skip the break part now. So this eigenvector here. So what we did was, after performing measurement, we get one of these eigenstates. One of these, this phi collapsed to one of these eigenstate. Did it? So this was how we manipulated it, and we encoded some information in it. From starting from cat 0, we ended up at something else. And this actually, since you know the qubit actually, I just told you that it has two level system. It can either be 0 or 1. So this ui here can either be state 1, or it can be either be state 0. So this was it. It did whatever I said is simple logic here. You can understand it anytime if you just spend the time thinking over it, right? So I guess we are done with it. There is one. Okay, before it, I guess I don't have the slides of gates, but I'm going to explain you about gates now. What are gates? Well, let me just have a blank slide. So is there any other doubt if I just check it out? Yes, got it. Great. Thank you. Okay. Okay, what was I doing is let me just take a blank slide and I talk about gates here. Now, what are gates? Similar to the gates that we studied we use in classical computing, but we to manipulate the bits, we have gates here. Now, in the Stern-Gerlach experiment, what I did was I measured along the x-axis, sorry, along the z-axis at first, right? I measured along the z-axis. Now, this measurement along the z-axis is actually called the Pauli Z gate. It is similar to it is actually the measuring with Pauli Z gate. It is applying Pauli Z gate and then measuring the state of qubit. It is similar to that. Wait a minute. See guys, there might be some confusion on these things because I don't have proper slides here. So if anything is wrong, I am asking to TA panel, they can point it out always, right? Just two. So while measuring along the z-axis, what we did was we applied this Pauli z gate. There is a name for it. Pauli z gate. We denote it as sigma z. Okay, and this actually, okay, let me just if you remember, I had some information about it in prior slides, some slides. Sorry, I have to go back all the way. Okay, in the matrices, I guess it was. So yeah, here it is. So, okay, I should have taken this image already. So I am just gonna explain it here, right? I'll explain these dates here only. So the when we measured along the z-axis, here it is. When we measured, when we did the Stern-Gerlach experiment and measured the spin along the z-axis, it was similar to Pauli z-gate. We represent it with this. Okay, and it has a matrix of form like this. So this gate is, as I said, every gate can be represented as matrix. So this is the matrix of Pauli Z gate. Now, when I apply this Pauli Z gate, when I apply this Z gate on any file, what am I doing is that doing a vector, sorry, I'm doing a matrix vector multiplication between these states. Okay, so this is going to be a matrix, this Z is a matrix, and this is going to be a file. Okay, wait a minute, there's something in the chat, I guess. Oh, you will get the PPT. I'll upload it already. Although I guess it is already uploaded there in the Discord. If you don't have it, I'll suggest you to join the Discord. There was a link sent to it, or otherwise, I don't know if you have any other arrangement of sending these PPTs. Okay, so please Discord is the only option. So now what I was talking about is if I apply the Z here on the state phi, I'm just doing vector matrix vector multiplication, right? And a matrix vector multiplication actually scales and rotates the vector, or it is used to transform a vector. It is used to transform a vector. Okay, simple thing. So if since it is used to transform a vector, what will be there is okay, but so it will change the state of this file. The resulting state, there would be a resulting state file where it is we have an eigen. So we'll leave it. We have an eigen value here. I can represent it as something a ground wall here. I'm just doing some pictorial representation. So we will have we will be manipulating this I, and we will get to another eigenvector actually. So yeah, and one thing might not be clear is that what okay, let me just not get into it. If there would be a doubt about it, I'll explain it later. Okay, so I don't want to puzzle you. Now, similarly, we can measure along the y-axis, and this would be called the Pauli Y gate. Okay, so if we perform Stern-Gerlach experiment or we measure this thing along y-axis, we get y. Actually, these are doing rotations. So the thing is that these are doing rotations. Okay, these are used to do rotations, I guess. If I am wrong, anybody can point me out if I get anything wrong, right? I'm not too confident about these things. Then comes Pauli X1, sorry, Pauli X. Pauli X is measuring in the x-axis. Okay, this inverts what it does is that it inverts the value of R measurement, R cubic. If I had 0 here and I applied, like we did right now, like if I applied X here, instead of that U gate, if I applied this Pauli X here, what will I get? I'm going to get 1 here. So what it did was it flipped the state. Instead of having, it changed the state from 0, it flipped it to 1. Great. So now, what I'm gonna tell you is that if again, if it was R1, it will convert it to. If I apply X here, it will convert it to. What will it convert to? It will convert it to 0. This is like bit flip, isn't it? It is like bit flip actually. NOT gate just did 1 to 0, and it is similarly doing. But this is a quantum NOT gate. You can understand it this way, right? Now, while using the Pauli z-axis, what does Pauli? It does the rotation about the z-axis. Okay. Now what I get is that now along the z-axis, actually, if I let me just go through the slide. Instead, I'll just move this slide later, so I don't have any further problems. Okay, just bear with me for a while. Okay, I guess it is on the end now. I'll do it properly. Just a second. Okay, there. So let me just, if I go through the Stern-Gerlach experiment, what we did was that, answer, yeah, what we did was that when we measured through to the, when we did the experiment on z-axis, what we could have said is that this is the positive axis and sorry, this is the negative axis, okay? And when we did it as this axis, what we can say is that this is 1 or this is 0. We can say it like this. Okay. Now this might seem a little confusing. What are we doing here? What is it? So what I'm going to say here is, what am I saying? These things are getting me confused because I don't have a side slide here. So I'll just I'll use my notes for explaining it. In just a minute. And yeah, don't be afraid if you do, that you will miss everything that I am teaching from the notes. I'll update the slides too. Okay, so suppose I was going to apply this X gate. What happened is that it changed the state of qubit from 0 to 1, right? It is what it did. But actually, by measuring through Z, we are taking the states as mm, wait a minute. Oh, shall I? Okay, I got an idea because things are getting a little messy. Let me just go forward because we are going to go through the quantum experience. There, these things are easy visually. So why have to go all such pain, right? So I'll just explain quantum advantage now. Quantum advantage here is that if it refers to the fact that quantum computing can solve some intense computational problems. Okay, intense. See, when what Abhigyan did was that he introduced something called postman problem, right? So what it was that if you have a postman and he has to deliver some item. So actually, he said that honey uses whatever it solved this problem using the quantum computer. So what actually what the thing actually is that Amazon, what does Amazon do? It delivers you the items, right? You shop on it, it delivers the items. So see, the postman problem is similar. So if you have a postman, if you have this guy postman, here, he has to deliver things to random addresses, and there are various paths that it can follow. It can go first here, then here, or I will change the color, or he can go first here, then he can go there, and he can go there, or he can go around the universe and then come here, then come here. So there are many paths. There are infinite number of paths, right? So what actually what the solution was that sorry, what the solution of this was, how quantum computer use was helpful is that, see, if we use a classical computer to find out which route would be the best possible ones. Okay, which would be the shortest ones, which would be the most efficient one. So a classical computer what will it do is that it is going to calculate every single possibility of the path. It will first calculate that what will happen if how much time will it take to go through here to here to here to here, or how much efficient is going through here to here doing is will be. So what I'm just saying is that it is going to calculate every single possible path that this postman can take. Okay, but a quantum computer, if this postman is a quantum, if it is a quantum postman, and it has to go through the paths right here. So what will happen is that if I have a wave function here that contains the information of all these paths. Let me say P1, it is path 1 plus path 2 to path n. Okay, infinite paths. Okay, there is again something, I guess. Great. So Daniel mentioned that it can be applied to logistic problems in e-commerce, and which is true, because in e-commerce you might have to find the best possible way to do something, right? You can do a research on it through internet. So, but you can use this for our quantum computers to just find the best possible answer to any problem. Okay, like here in the postman problem. So we had a superposition of where if it was a quantum state, the for this if this quantum wave function had all these paths that this postman can take, then what will happen is that if we apply the best, let me take a B operator, which says that it will give out the best path from all these paths that this postman can take. So what will happen is that I apply this B over here and apply it to this whole state. Now, see, what I said was that it will a classical computer will first apply this B to to P1, then it will apply B to the P2 up to Bn. It will take n number of terms, n number of computational rounds, or it will take n number of operations to find the solution for this problem. But since this phi is a linear combination, applying this B will at once apply this applying this operator B to phi will at once apply this operator to every single of these states of these possible outcomes, and give out the best just in one operation. Okay, instead of having so it will collapse to suppose the p third was the best path, so it gave us an outcome here. So it did it in one computation, right? Just applied one gate and it happened. Although actually two, because we have a measurement also. So no, let's not get deep into it. So what it simply did was in single operation we were able to successfully compute it. But a classical computer would have taken n times of of operations, right? So in this way, you will see that these are very fast. We can have advantage. We can have a quantum advantage. This is called quantum advantage, that we can quickly solve many computationally intensive problems very quickly in a reasonable time. It just did in one operation. It will take very reasonable time. Whereas going through all these in n number of paths will take forever for any quantum computer. Great. It is a simple thing, and a real life example here also is along with that e-commerce problems and finding the best route for our airplane, or all these things, finding the best schedule for our flights. Along with this, there is something called factoring large integers. RSA uses large integers to keep our communication secure. So Shor's algorithm actually helps factorizing them, and this is in this way this breaks down the RSA, right? So you would have heard about it. We will go into it, I guess, in tomorrow's slide where Vishal will teach you about it. I guess I am not sure. He might only just brief about it. Okay, so this was an example that I want to give you. So this was quantum advantage. The reason behind it was I have told, because because of the superposition. This is actually superposition doing all the magic here. So because of the superposition, we can apply an operator. We can do an operation parallelly to every state. Parallelly means at once to every state instead of doing it one by one. So this is quantum advantage. So I think it will be clear now. So now comes noise. Noise is a quantum computing specific term actually, but noise actually is uncertainty. We know that quantum mechanics is uncertain, right? Heisenberg's uncertainty principle got it. Okay, there's something else. Yes, GPUs do parallel computing, but they use bits. They use bits, right? Instead, there is a limit to the what shall I say? Okay, if you come, I'll suggest you to go to type search in Google that how do we get quantum advantage. So it will, because I have to explain you quantum. Sorry, I have been experienced to we have to go there too. So I won't take deep into it now. I've done with this topic. You shall go and search about quantum advantage. How is it beneficial? And yeah, one thing that Avigyan said was that when how many qubits do we need? Yeah, it might also help your answer that how many qubits do we need to represent some information, right? So to represent two, one and zero, to represent this, we will need classical bits, right? We will need two classical bits. Okay. Now, if we have to do this here, it will need four classical bits. If I had to do 1010 here, it will need again four classical bits. But if you see, one thing great about quantum computing is that I can use a qubit. Sorry, I can use a qubit to. Okay, let me just say, yeah, I can use a qubit to, like, suppose I use four qubits, then I can how many states can I write with it? Okay, let me tell it in another way, right? Suppose I have a qubit here. Let me call it 5. How many values can it take? It can take be either 1 and it can either be 0. But after measurement, before measurement, it is both 1 plus 0, right? It is both 1 plus 0. It is right. But a simple bit, what happens is that it can either be 1 and 0 every time. All the time, it is either 1 or either 0. It cannot be anything in between. But our quantum state can be, right? So, if I had to represent, if I had one qubit, I can at once, in one single time, I can have these beats. I can have 1 and 0 represented at once. Here it will wait. I'm saying that in the case of bits, I will have to use two bits, one to represent the one to represent the zero, and then I will have to perform computation on it. Okay, then I will have to perform computation on it. But in this, I can have only one qubit in 5 1. Let me say 5 1, and I can work on it. I can apply any gate to it. I can do any measurement. Sorry, I can do any operation on it, and that operation would be done on both these states, on 0 and 1 at once. Would be done on 0 and 1 at once because they are in a superposition, right? Similarly, what I can have is I can have I can have two qubits here. I can have 5 1 5 2. Let me say. Sorry. Let me just say for it Q here. I'll just call it qubit one here. So I can have qubit two 1 and qubit 2 here. I have two qubits now. What will be the outcome here? Oh, just yes, my data is finished up. I'll switch my this network. Okay, just it goes again, then I'll switch it. Okay. If you are not able to hear me, then you shall tell me. Okay. I'll share my screen again. Let me just change it already. I'll be let me do this. So here, yeah. So what I was talking about it now, I have two qubits here. So what can happen? The first.
Hello, Lokesh. Hello, Lokesh. Sorry for the inconvenience, guys. Lokesh has some network issues. He'll be right back.
Hey, I think I'm back now, right? Fine now.
Yep, we can
Can
hear
you
you.
guys hear me?
Yep,
And can you see the screen I shared?
yep, we can.
Okay, let me get back now. Still with some time loading. Yeah, just a while, just a while. Okay, so what I was saying is that if you have two qubits here, what can happen? First, one thing can happen that the first qubit is zero and the second qubit is also zero. We can have both as zero. Then another state that it could be, see, we are expressing it as linear combination here, right? So what can we have is that first as one, the second as zero, then second as first as zero, second as one, and both as one. So see, how many how many qubits did it take to represent these states? Just two qubits represented four states here. But if I had to represent these states with bits, I'll need separate bits for each of them. I'll need two for it, two for this one, two for this one, two for this one. I'll need 8 bits. So this is why it is computationally very, this is also a advantage of quantum computers, right? We can actually, it can be, they can be used to operate on various amount of information at once. Okay, you can understand it this way. Okay, so there is a formula for it that how many states can we represent, how many qubits do we need to represent a state, or how many states can we represent with a qubit. We can represent 2n, I guess it is the formula. So if when we had, okay, there's something again on the chat. We just check it out if there is a doubt. Yeah. So now, how many did we? How many? What shall I say? Okay, with these two qubits, how many states did they represent? They represented four states, right? I can just say it as two. I had two qubits. The n is number of qubits, I guess there. So we'll get four. We can use four states to here. Okay, this might not have made sense. If there is anything I can improve, because I don't know how to tell it. Okay, leave it. We'll just leave it. I can read it later. You can check this out. I have told you that you can always search quantum advantage in what is quantum advantage in Google. You will get your things clear. Oh, now let us go to quantum stack. What is a stack actually? What is a stack in a normal sense? A stack is just putting some things over and over and over and over, right? Similar is the stack here. No, the stack thing is simple in classical. Classically, it is also the same thing, and just there are some things changed in quantum computing. In classical computing, at the base level, you have transistors, you have bits, and all these. So we can call it hardware, right? Then we go from hardware, we go from software. Okay, we go from the we go to the software level. Okay, and these softwares are encoded using languages like Python, Java, all these. So all these things, these interface, these levels of how the quantum, how computing operates can be called, can be referred to as quantum stack. Like if I was to go through, so first of all, what you do to work on quantum computer, you first give an input. You give an input. It went to a hardware first, the input hardware. Then it went to the software. The software understood it. It understood that it as binary. It understood that binary, and then applied it on the level of the bits at the transistor level. It applied it on that. So this is a simple example of a stack. The stack can be of various ways. You can look at it in various ways. There can be many examples of stack. You can always check classical and quantum stack too in Google. Okay. So how does quantum stack looks like? first we have a application. This is the software part. Then we have a hardware part, right? There also in classical computing we have a software part and a hardware part. Bits come into the play. Bits and our gates are the hardware part, and the input things are the hardware parts, and the software parts are all those softwares that are inside. Okay. The next thing that I'm telling is, yeah. So first thing is application. The application is the interface, I guess. The interface that we are working on. Like we will be working with IBM quantum experience. Okay. Now then comes algorithm level. Okay. We run any algorithm here. We use any algorithm. What we do is we type in any algorithm that we want. Then it is converted to programming language. Okay, so that is actually in our we use it as we write these algorithms in programming language, and then they are converted to assembly language. They are bits. They are converted. Like if I wrote my code in C++, then I wrote the code in C++. It understood it, it interpreted or it compiled it, and into the ones and zeros, into the binary format. And this ones and zeros is what our machine understand. This is the machine. This is what happens. So I am not able to explain it properly here, but this you can just get a little sense of it. But I am going to say, because this image is actually a bit confusing for me too, because I didn't create it, right. So what I am gonna tell you now is, in quantum mechanics, what happens is that we do this part. We do this part. This part is simple enough. I go to the quantum IBM quantum experience, I guess. I write my algorithm here in with programming language Python. I use my Python language to write my program. It is then interpreted. Python is uses interpreter, so it is interpreted, and it is written into assembly language. Or understand? It is written into ones and zeros, binary. Okay. Then what happens is that in this IBM we are actually working with a cloud interface, right? So it is sent to the actual hardware now. Okay. This hardware, what happens is that this hardware now interprets everything. This hardware, there now, actually this part was a classical part. If you notice that I am working on a classical computer and using all this. Okay, I am working on a classical computer and using all these things. So the classical part, this was the classical part. I was working on a classical part. Now what comes is that the machine here, up to this part, up to the assembly language part. Okay, before this, I wrote my code in Python, and now it was sent to the IBM quantum servers. So, okay, I should write it properly. I'll say, yeah. So this was now sent to IBM servers. Okay, IBM servers, and there were again some classical computers interpreting it and creating some machine code. Okay, about it. Now what they do is that they create some machine code of how are we going to, how is the what operations are we going to perform on quantum computer. Since quantum computer cannot understand the classical language, right? It cannot understand 1001. Okay, it needs something else. Okay, so now it goes to instruction set architecture. The instructions are created from what I said. The instructions for the quantum computer to work are created in IBM server. There they are created. Then it goes to micro architecture, which means is that the structure, the whole setup of our quantum computer. It goes there. Then gates are applied on the devices on the qubit level. And okay, this is the physics here, represents the quantum mechanics that is working on there. Basically, because at the initial end, what is acting, what is being all this dance, it's quantum mechanics, right? So this is an example of stack. This is what happens when we do this. Represents a stack in a broader sense. You can it could have been better, but let us just bear with it right now. Okay, the next thing I guess is just going through the IBM quantum experience, right? So the break that I was talking, I need to set up my quantum experience. Or first, let me do one thing. We have to not only go through this. I am gonna do Replit one also. I'm gonna show you how to work on Replit or how to just log into Replit. We are going to use it in tomorrow's session. So let's first start with Replit. Okay. So the website for it is repl.io. dot it here. I'm just type rebel dot it and press enter. And yeah, guys, if there are any questions still now, we have concluded our mechanics section. If there is something I can sort that out. Okay, I guess there isn't. So now this is the interface of our IDE. So IDE is something where we write code in it. What it does is that, okay, there are, I guess. Okay. There aren't. So what an IDE does is that we write code in it and it uses the interpreter or compiler and converts it into machine code. Okay, it is kind of an editor. We have an editor here. So it is called IDE full form is I am a bit confused about the full form. I forgot. It is not coming. It is tip of the tongue here, but it's not coming. So leave it. Okay. What we call it is something environment. I guess leave it. So it is an IDE here. We do our coding here. So what it is, you don't need to install anything. This is a simple way. This is a browser-based IDE. So we can write just through our browser, through our Chrome and else. Okay. So what I'm gonna do is you need to create an account here. So you will, I'm gonna just log in, but what you can do is you can sign up. You will you can just sign up with your Google, your GitHub account, your Facebook too. Okay. Or you can just use your email simply. You can just have your username. I am writing look great here. Just simple. Okay. And I'll write my email, whatever it is. I can write my email here. You know how to write email, right? And I'll just create a password. And then what I'll do is, since I'm not written proper email, so it is showing an error. And then I'll have to create a password for it. I guess. Okay, let me just suppose this was my email. So I'll then create a password here. Let me just write any password. We create a strong password here. I just wrote a password and click this create account. So it will be fine now. Okay, you will have an ID, your ID replic setup. But since I already have an account, what I'm gonna do is I'm gonna log in. I'm just gonna log in. Okay, I'm gonna log in with my Google, or you can just type your username and password there. But I prefer doing all the with Google. So this is how the Replit interface looks like once you are logged in. There are some create option there. It contains many languages here. You can create in any language, and what we are going to use is Python here. Okay, Python. So let us get back here again. Yeah. So here are various languages that you can work with. Options here written are Node.js, C++, Python, and we are going to work with Python. Okay. Now here this panel here is showing recent. Actually, I coded some things here, so it actually gives some random names like the sandy grizzled quadrants doesn't mean anything, right? Okay, yeah, it doesn't mean anything. It doesn't make sense. So it gives such random names to your programs that you are going to write. But you can always change it later. Yeah, integrated development environment. Thank you, Aryan. I forgot the time. Yeah, so ID is integrated development environment. Okay, so now what I do is here, sorry, there are some things here going on because just to have you interact with other people's, this is what Replit is giving you. You can also learn many things here going through this learn panel, and you can explore any time. But what is important here is that how we're gonna code. Tomorrow, when you can work along with Vishal when he'll be coding, or Vishal and Freya when they will be coding, or you can just watch and you can code that later. Okay. So if I to create a new one, I'll just create and click on Python since we are going to work with Python. So it gave it a random name, okay? And I created a REPL. We call it a REPL here in Replit, okay? And I really find it very useful. The Replit, I find it very useful. I don't need to download any specific libraries for it, and I can just work with my browser. So you can always use it, okay? Now this is the editor portion. Here is its editor, and the main.py file is open here. This is the console. Suppose you'll know how what we am I gonna do if you know Python. I am just typing printing something, and if you don't, you'll learn it tomorrow. Okay. So I'm just gonna print that my name is Lokesh. Sorry for the typo. So I'm doing my name is location. Okay. Now if I print it, how can I run? I'll just click on this run command here, and this will run this code. It will convert it will interpret as a machine code and show me the output here. It will print it. I'm asking it to print, so it will follow my command here, and the output is shown here in this console. Here is the console. Okay. Don't get into the shell part because shell might need to run it. Actually, shell might need a lot of knowledge of computers. Okay, so simply just a shortcut key here is a hotkey here is press Control and Enter. So what is now doing? Yeah, you see it has printed what I asked it to print. So this is the basic way our applet works. We can code anything in it. I was just doing a walkthrough here, so we are done with it, I guess. Okay, let me just get back. So I'll just close this separate thing. And now what we are going to do is we are going into the IBM Quantum Experience. So just type in IBM Quantum Experience. The first one here comes. Just click in it. What do we have now? Real quantum computers right at your fingerprints. Literally said, and it is true. You can work with quantum computers there. And how we are many things we are going to study tomorrow. So be excited about it. Here it is asking us to sign in with IBM ID, but I actually am going to use my Google ID because I don't remember the password of my IBM ID, so it might create some problem. Oh yeah, first time instead, yeah. Oh God, I'm already here. So let me just log out again. Since few of you would be having any IBM account, the simple thing is go and into the create an IBM account part and just go and create an account. Okay. Yes, you need an IBM ID. If you don't have an IBM ID, go create an IBM ID. You will have to use your email. I'm using mine here. I already have an email, but I'm just giving you some walkthrough. So I'll type mine. You can. Okay, so I'll use some other. Okay, I'll use some other. It is showing an error while using my this email ID. So I'll use some other. I'll use my brother's account. Okay. So now I'm gonna write my name. Sorry, I'm gonna write my name and then my second. And I don't use a second name, so I'm just putting a dot here. Or probably it won't take a dot, so I can put just anything here. Okay. Now I need a password that should be 8 characters minimum, one lowercase, uppercase. All these conditions should be satisfied. Basic things, just do it. Can you have your residency I am in India, so you can choose from the list drop down here, and then you will just click next. You will have to verify your email account. While verifying, it will send an email to you. You open that email and verify your account. If everything will be settled in. Then again, what you need is you can have to log in. You can also okay, but you have to just log in now. So like I did, what you can do is you can have your IBM ID, or you can use Google, GitHub, LinkedIn, Twitter, and many things. Okay, just do it. I'm using my Google here. So great, I am in. And this is our beautiful quantum experience. This is what it looks like. Here at this side are my notifications. Upgrade to IBM Quantum Privacy page, this and this, all this. Yeah, here is a notification about this is our quantum computer named Melbourne. Actually, you'll see that many of the quantum computers are named after cities. Actually, so we'll see all of them in a while. So there are some notifications here. It gives service alerts. It is given since this service is going to retire, so it is saying this is telling this is giving us an alert. Okay. Now here are some things. The first thing is IBM Quantum Composer, and it is very interesting thing that I want to show you about. I'll be working with it in a while, but let's first go to IBM Quantum Lab. Okay. I did, this is what you'll be working tomorrow in. Okay, this lab actually is Jupyter Notebook actually. I can just show you this interface first. What it is saying is run on circuits algorithms by IBM quantum services. Let me do the view all. This panel actually tells me the devices that are available for me to run my code. Okay, so that programs, there are separate sample programs here, sample program, just something written. Okay, then is VQE. It is actually variational quantum eigensolver. These are algorithms that give us minimum eigenvalue for some things. Okay, just and there are other two algorithms written here. So this is just giving me the program that I can run. Okay, now our systems, the quantum computers that I can have. And one thing is written simulator too. I'll explain it in a bit. Okay. First one is IBM Montreal. I am not gonna tell all of them, but the thing is that there are only systems that can be accessed. There are some systems that can only be accessed by the members of IBM, or they need some what shall I say, some status to access it. Okay, the free members or people, simple people like it cannot access. So those that I can access, and those that I cannot access are shown with this lock here. You do not have an access. Okay, I don't have the access to these systems, but there are some that I can access. So they are listed here in your systems. So my systems means I can use them. First is IBM Santiago, Athens. There is Manila, Melbourne, and this Melbourne is going to retire. Okay, then is Belém, Quito, whatever they are. Their name is, they are just named. And don't get confused. They are actually not named on the cities. They are based on. They were first thought of doing. It was thought first that they'll name it that way, but since it is not anymore, it is not their agenda anymore. Now, what is it saying actually? Is that it is saying that is it online? Yeah, system is online. I can work with it. Processor type Falcon R4L. This is the processor that it is using. Then the number of qubits in the processor are 5 qubits. And quantum volume actually, this thing here tells us that this thing here, quantum volume, tells us that how complex problems can be solved. How does it tell us? We won't go through it. Maybe you will have to go to a higher uh, workshop for it, or maybe we can just brief it tomorrow. I don't know if you're going to do that. So, but what it tells us is that this quantum, how complicated tasks can I perform? How many gates can I apply? How the number of gates can I apply and get a reasonable result? Oh, wait a minute, guys! I forgot, I guess, to explain you noise. Right? This would be very easier. This would have been. This will get easier when I explain you noise. So let me just. Sorry, but get back to my QBasic slide, and I was not clear about the noise. So let me just do it. And we are going to see some noise things here also. So let me just tell you, explain it easily. So quantum noise actually is because of uncertainty of physical quantity. Okay, it is because of uncertainty that uncertainty principle brings, or it is about due to noise actually is inherent to the quantum system. We cannot always cancel out every noise, but we can, although this is our aim to have a noise-free system, but right now there is noise because of various reasons. First reason is the qubit. What material is it made of? What is it used with? How it is formed? I mean, which type it is? Like we can have superconducting qubits. They can have noise because of electromagnetic interaction. Like even the cosmic waves from the universe that are always there, they create noise on superconducting qubits. And then there is the topological qubits that actually who told you about I guess guest lecturer Abhigyan told about them, right? So actually, they are the least noisy systems that are possible, but they are just mere concepts. They actually use relativity, as far as I know. So they are just mere concepts. So they are least probable, least exposed to noise. Okay, and there can be one thing. There is short noise. There can be noise because of various reasons. It can be because of heat also, right? Because see, noise when we are doing our, okay, you don't have. I have not told you something, but in a while we'll get into it. We'll get how a system is set up, how quantum hardware is set up. Okay. So the short noise here that is written here. What is short noise? Actually is the number of measurements. How many measurements do you do? Since everything is probabilistic, while measuring, we perform our circuit to get a reasonable measurement. We perform our circuit a lot of times. Now, why do we do it? So the thing actually is that the phi state can collapse to 0, 1, and up to how many any states that there are present. Okay, it can collapse to them. But see, although the coefficients here, beta, they define, there was probability of falling into this state, but it is not always sure, right? It is really not sure that it will always fall into state 0. Sometimes it will get into state 1. Sometimes due to noise, it can get into any unexpected state. So this is what noise does. This is what noise does. Wait. So if suppose I took only one measurement and I wanted an answer, I expected that the answer would be 0, but due to some error, it happened to be 1. So I think that my algorithm failed, right? So how can we improve it? Instead of taking one shot, we take a lot of shots. Okay, we'll see this shots thing. It will come up in the IBM quantum experience in a while. Okay, so what this shot does is that most of the times, how many times? See, if you take a lot of coin tosses, although the probability of heads and tails is always 1/2, but if you do a lot of trials and you want heads to come and it is more probabilistic that heads will come, then most of the time heads is coming. If it is a rigged coin, okay, if it is not uh, a fair coin, if it is a rigged coin, then X side is heavier and H side is more probable of coming. So it will have mostly H, but there will be times we will get T. Then there will be H, 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 and H. And our expected value, what we want is H here, right? But we are getting some unexpected result also. So if I just took first 3 measurements, if I just measured it 3 times, if the shots were 3, then I'll get 1 wrong here and 2 correct here. If I just took 1, I'll get 1 correct. If I take more of them instead of just 1 to 3, if I take all these measurements, then the probability, then the outcome becomes better. You'll see if I draw the probability distribution, a distribution of the outcome here. So 1, 2, 3, 4, 5, 6, 7, 8. 8 times did I get our heads, and 2 times I get tails, right? So our answer would be this one. This is why, so that we can get the better answer. We don't actually get a problem about it. Wait a minute, something is in the chat. Let me just see. Every state that is measured is removed the set of. So by short noise, you mean each measurement we make, every state that is measured is removed from the set of the quantum states successfully, heading us to the most appropriate outcome. Oh, actually, I didn't understand your language, so right now, but I look into it. Your chat, I look into it, and I might write it in the doubts section of that is called. Okay, but what I actually mean about it, if you are if this makes sense, I was meaning is that if noise due to limited measurements that can be made, because see, if you are doing infinite number of measurements, right? If you are doing infinite number of measurements, then we can say that the improbable outcomes, the non-unwanted outcomes, because they have less probability, right? So improbable outcomes will be very less. They will come. We will see very less of them. And if we, but since and the answer, mostly the answer would be near to our 100% of the outcome that we wanted. Will be near to 100%, and a few times will we get unexpected result, right? But since the shots here are limited, what I mean is that you cannot perform infinite measurements in a quantum computer, right? Actually, infinite is just a concept, actually, right? So we can maximally perform 8,000 shots, right? Till I know, until I know. Right now, I'll show you just two. So out of 8,000, we can, if I perform only 1,000 shots, then there would be less number of answers that are correct, and there would be some answers that are not correct. But as I increase the number of shots, I grow it to 2000, the number of H will increase, and the Y will increase relatively, it will increase very much, and the number of shots, unwanted ones, will increase very less. So after the result, the outcome, what will I get would be very much the one I want, and very less the one that I don't want. We'll see it in the quantum IBM experience too. So by increasing the number of shots, we can reduce this noise. We can actually this is actually not a proper noise to say. It is not an error that comes. It is something that is inherent to the quantum systems due to the limited number of shots that we can perform. Okay, every time you cannot get rid of this thing. Okay, but you can you cannot get rid of this thing until you apply some optimization to it. Okay, so this was it. This was noise. Now what I gonna go I'm going to go back to my IBM quantum experience. Yeah, this one I was using. So yeah, so now 32 quantum, I was telling you about the quantum volume. It shows us without getting any unwanted result. Without, see, there are every time we perform measurement, there is also some noise. Okay, I guess you are referring to that thing. I guess, yeah. So every time we have, because our gates and all the things are not perfect. The reason is that they are not very perfect. So there are many. So they they cause some noise. They cause some errors in our measurements. Okay, these errors by meaning is that these errors will cause deviation from our wanted result to our unwanted result. More errors, more unwanted results will show up just because of these errors. They are not inherent things. They are not because of short. They are just because of imperfect quantum systems that we have. Okay, understand this thing. Okay, now this but so this 32 volume quantum volume, what it is saying is that it is telling us that how complex how computation can be performed without be incurring a lot of that error, that noise due to the imperfections. Okay, the error that the gates will include. Since so I'll explain it in a while because we are going to create a little circuit right now. So these are the quantum computers that you can work on, and I'll go back. No, yeah, there is something called simulators here, right? See, simulators actually are classical emulators, classical computers that perform the quantum simulation. They perform the simulation of our quantum computer. They simulate. They act like they are quantum computers, right? Now you will see that how is it possible? How can a classical thing work as a quantum thing, right? As a quantum computer. Actually, the thing that happens is that we read the maths about, right? We did the maths. We know, actually, we were doing some calculation. We read the maths here. So using that maths, these simulators, what they do is that they just follow that maths that we studied about. They solve using that maths. Now, the problem, as the algorithm becomes more complex, the more to simulate just 5,000 qubits, we need a lot number of qubits. And how many qubits do we need? At basic, I guess, given we can relate it this way. Hey, is somebody drawing here? Nitin Nayak, I can see you annotating the slide. Please don't do it. Uh, Guys, if you can uh, stop anything like this happening, if there is a chance, it might be problematic. Yeah, thank you. Remove these two. Thank you, Nitin. So what am I saying? What was I saying actually is that we read that. Sorry. Yeah. What are you saying that we saw that just to represent a small data, I'm sorry, to represent a large data, we needed a lot of bits, right? But similarly, so in case, okay, no problem, Nitin, it happens, no problem. So similarly, to work on a specific data of a quantum level, we will need a lot of a lot of bits. So these classical computers are kind of supercomputers. They have a lot of bits. So that is using them, they can simulate some limited number of qubits, like simulator stabilizer actually can simulate work with 500 qubits. And we have a Cosm simulator that has the maximum one of actually this Cosm simulator is a very useful simulator. We are going to use it, and what it does is that it acts as uh, it simulates a quantum computer like identically. It totally acts as a quantum computer, and what it can perform is the maximum qubits it can simulate is 32. Okay, you cannot go further than it. You cannot add more than that qubits to a circuit by simulating this. Similarly, we have simulator, state vector simulator, MVPS stabilizer, and these things just focus on these two right now because actually these are going to be important for tomorrow's session. Great. Now what we have is we can go back to the, yeah, there is the panel menu. Now I have few things here. Let me just go back to the dashboard. Right. So, okay, I'll just delete all this annotation here. So this is where I saw all these systems, the systems I have, simulators I have access to 9 simulators. Total quantum systems are 32 in IBM, and there are 5 simulators there. Okay. Then comes the part of reservation. Reservation, this actually is the jobs that are reserved right now. We can just leave it. We'll see why we work. And this shows pending and completing. I don't actually know what this reservation do. So it's somebody that they can help me out, okay? But till then, I'll go with this recent jobs section. This tells us when we ask a quantum computer to run, when we send our code to a quantum computer, it is added as a job here. It is given as a job to the quantum computer, and that quantum computer has. I actually worked with some. I made some circuits and just tried out them out. So these are the jobs completed that actually that were completed by that were actually run on the quantum computer. So these are the pending, these are the completed jobs. And if I just have a quantum compute, make a new circuit and send it to the quantum computer, it will first go to something called a queue. So well, actually, since to a quantum computer, a lot of circuits are coming to be run. A lot of everyone is sending all around the world. So it just works. So it just creates a queue. The first one coming, the first one is. I mean, they just are kept in a queue and work, and then they are run one by one. Okay, simple thing, easy. Okay, now what can I do is we are going to the quantum lab first instead of
Lokesh?
quantum yeah.
Yeah, so just a reminder that you have 15 minutes left.
Okay, so I just skipped with quantum lab. We are actually this quantum lab is that it allows you to code your with Python. It allows you to code. It is a notebook. It is actually Jupyter notebook integration where the Qiskit library is already installed, and we can type our code here, our quantum code here, right. So all this you will go tomorrow, so don't worry about it. I am just going to go to the quantum composer, which is IBM quantum composer. If I open it, what we get is, yeah, if I open it, this is a pretty beautiful circuit that I can see. This is the toolbox that I can have, and here are some gates applied here. Many of the gates we have not studied about, but no, I am not going to teach you quantum algorithms, but there are some things that maybe it's tomorrow. Wait for tomorrow. Maybe Vishal's plan makes up his mind of teaching you that. So just wait for tomorrow. So here are some gates. This one is Hadamard gate or edge gate. Hadamard gate puts a quantum system into superposition. Now, let me just create. What we do is we just pick the gates here and add to these things that this what you can see here. So let me just tell you what it is. This is a dashboard. This is our interface that I can say. Let me zoom out a bit. It is, I guess, it is zoomed in too much. Yeah. Now it will be visible quite well. So here is, you can see here it is written Q naught, Q0, Q1, Q2. These are the number of qubits actually. This is the first qubit. And we pick a gate and we apply, we just put it here, drop it here. to see that this qubit, what will this qubit become after a while? Okay, so we are applying this H gate on this first qubit. Then we can apply a gate to the second qubit too. Right? Sorry, it is an control. Sorry, it is we can say control gate. You are going to study it tomorrow, so don't panic about it. I just took a Hadamard gate here, and what I did now is I'm taking our NOT gate and I am applying it to the qubit second. What you do is pick up gate and drop it down on here on the qubit that you want to apply it to. Simple. Okay, just nothing else. Now you will see that there is a C3 written here. So this region here is the quantum register here. It contains it registers your qubits. And down here is the classical register. So after measurement, what we need is that after measurement, our qubits state collapse, and we need to assign the answer for measurement should be assigned to some classical bits, right? To store them. Okay, so what we do is that these are the classical. This denotes the classical bit. Now, if I do one thing, see here is measurement. You'll see here. This is what I was talking about. You saw something called measurement here. I showed it in the slide also. So this is our measurement, and when I apply the measurement, there is a line coming here, and it is showing 0 here. So what it is showing is that our I have applied Hadamard gate here, and then after performing the measurement, the outcome would be registered to qubit 0. Okay, it is going to be registered to qubit 0. Here 0 shows the number, the qubit, sorry, the classical bit. Sorry, the outcome would be registered to classical bit. And which bit? The classical bit 0. Uh, in this 0 and 2 is just index, the numbering of the bits. Now, if I do a measurement on the third one, it is gonna, and then I do a measurement to the second. So we start with 0, 1, and 2. This is our measurement. It is being stored in C0. It is being stored in classical 1, 0. They are just this classical bit is corresponding to the qubit we are using. So Q2 is being stored at classical bit 2. Okay, so simple thing. This was it. Now, what I'm going to do is let me just clear all this. Okay, I'll just delete these qubits. This is the delete option here. You just have to hover your this cursor around the qubit, and there is a delete option. You can just click it and delete all the qubits you want. And then there only one qubit can remain here. I just remove it. I can remove it. Yeah, I just removed everything. I have one qubit left, and what I'm going to do is I just talk you about the X gate, right? This is our X gate. This is our NOT gate, we say. This is our X gate. What it does, that it flips my state. If we have a 0 at the starting, it gives a 1 here. And we'll see how it happens. But before that, let's see. Down here, there are some things that you might be willing to know. There first here is the state vector being shown here. So state vector and there is an option of probabilities. Wait a minute. Just second. I'll move this tab here. Yeah. So what here is the graphical representation. First in order of in the state vector, in the order of state vector. I guess tomorrow somebody can brief you about clear about your this state vector thing. What is state vector? I'm a bit confused about it right now. So although you are gonna go through all this tomorrow too. So not just clear, not just a okay, you will study many things tomorrow, so I'll just complete it simply. So it is just graphical representation of what are we going to get. Okay, so in computing quantum circuit, Nitin, I'm not getting your question. Okay, can you explain why do we need to uncompute in quantum circuit? Okay, so someone's gonna from the TA is gonna explain that because I'm running out of time. So
Yes.
please attend.
Also, we'll be